today. With a hygienic mess named Annapurna, well-furnished hostels with single and double rooms, mechanized laundry, 24/7 water supply, complete power backup, and Wi-Fi connectivity, we ensure that students feel at home while they're away from home. The overall growth in personality and confidence is taken care by conduct of debates, declamation contests, and a host of indoor and outdoor games. NCC Wing for Girls and a vibrant youth club that organizes popular sports festival called Padakram, literally festival and cultural festival, which further heightens their energy levels. They're also encouraged to develop independence in thought and action, as well as trained to deploy appropriate technology paradigms for given tasks, explore new horizons, and lead teams to solve complex problems. With our learner-centric educational process, students are free to find their own paths and learn their way to limitless opportunities that awaits them. So be a part of JP University of Information Technology, Waknaghat, Himachal Pradesh, to be the leaders in innovation, entrepreneurship, creativity, and management. Because this is where we engineer lifelong learners.
Ladies and gentlemen, Department of Civil Engineering, JP University of Information Technology, Waknaghat, Solan, Himachal Pradesh, in collaboration with Institution of Engineers, Shimla Chapter, Indian Geotechnical Society, Shimla Chapter, Atria Institute of Technology, Bangalore, the Institution of Civil Engineers, India, and Indian Green Building Council, IGBC, Chandigarh Chapter, welcomes you all for the first international conference on structures, materials, and construction, shortly known as ICSMC 2021. On behalf of the organizing committee of ICSMC, I, Dr. Tanmay Gupta, will be your host for the conference for next 2 days. It is my great pleasure to introduce the distinguished guest at the virtual main table, starting with our chief guest, Dr. Konkyan Howe, from Department of Civil and Environmental Engineering at National University of Singapore. A very warm welcome to you, sir. I would also like to welcome our Honorable Vice Chancellor and Patron of ICSMC 2021, Professor Dr. Rajendra Kumar Sharma. Our warm welcome is extended to Engineer S.L. Swami. He is the Chairman of Institution of Civil Engineers, India. Further, Dr. T.N. Srinivas, the Principal of Atria Institute of Technology, Bangalore. Engineer Pankaj Dadwal, he is the Chairman of Institution of Engineers, India, Shimla Chapter. Architect Jeet Kumar Gupta ji, Chairman IGBC Chandigarh Chapter. Professor Ashok Kumar Gupta, Chairman Indian Geotechnical Society, Shimla Chapter, and Dean Academics and Research, JUIT. Professor Ashish Kumar, HOD, Civil Engineering Department, JUIT, and all the reviewers, session chairs, authors, listeners, and the members who have worked tirelessly to make this event possible. A very warm welcome to all of you. So, before moving ahead, I like the permission of Chief Guest and Vice Chancellor JUIT to kindly allow us to go ahead with the virtual ribbon cutting ceremony. With your permission, sir?
Please go ahead.
Yes, sir.
Yeah, please go ahead. Yeah.
ICSMC 2021 is indeed a huge collaborative effort with the aim of providing a dynamic platform to share the latest structural engineering highlights and achievements to the conference participants. The journey of the conference began in trying COVID times during lockdown period in 2020 with a clear motivation to bridge the existing gap in the field of modern construction between academic knowledge and ground reality, and providing the informations on innovation in structural design, new construction materials, and construction techniques. In order to fulfill this ambition, we needed to have a gathering under one roof of various researchers, academicians, companies, producers, constructors, and practicing engineers with our students, which was not possible alone. So, by the grace of God, the word of the conference spread very fast, and it attracted association from eminent institutes like IC India, IISC Shimla chapter, AIT Bangalore, IGS Shimla chapter, and IGBC Chandigarh chapter, who are our partner institutes in this conference. We are indeed grateful to all our partner institutes for representing the conference on an international stage and attracting renowned publication house like Springer to have the selected proceedings of the conference in its Scopus Index book, Lecture Notes in Civil Engineering. We, as structural and construction engineers, have daily impact on a wider society. The construction, engineering, and the industry is rapidly developing by reducing construction costs, by having sustainable approach to reduce burden on the environment, and by empowering the global infrastructure gap and boosting the economy. While most other industries have undergone tremendous changes over the last few decades and have reaped the benefits of process and product innovations, the engineering and construction sector has been hesitant about to fully embrace the latest technological opportunities and for improving productivity and efficiency. Thanks to digitization, innovation technologies, and new construction techniques, considering the rapid emergence of the augmented reality, drones, 3D scanning and printing, building information modeling, autonomous equipments, and advanced building materials, all of them which are having a reach of market maturity, now we can adopt and exploit these innovations in engineering and construction sector that can boost our productivity and streamline the project management and procedures to enhance the quality and safety. To capture all of this potential, a committed and concerned effort by academicians and industry across many aspects, from technology to operations to strategy, was required in a general way. ICSMC 2021 is such one effort where various keynote and technical sessions will assess the current progress and state-of-the-art technique in structural experimentation, smart materials, and structural technology. The vision of the conference started with to provide a unique international platform and forum for academicians, researchers, professionals, and students engaged in the field of structural design, construction, and material to share their experiences and exchanges in the ideas pertaining to innovations in design and construction practices with the use of new material. ICSMC 2021 in this effort attracted more than 400 entries from India and abroad for this first iteration of the conference, out of which 100 selected papers will be presented in next 2 days. The conference is having 10 keynote sessions from distinguished speakers around the globe and a total of 12 technical sessions in running pre-lunch and post-lunch sessions on both the days. Our keynote speakers include our chief guest for today, Dr. Konkyan Howe from National University of Singapore, and he will be delivering his talk on chemical admixtures for autonomous healing in concrete, the past, present, and the future. In other keynotes, we have Mr. Animesh Chen from JCC Infra Private Limited. He will be delivering the industry keynote talk on bridging the gap between the academia and the construction industry. We have the honor of having Professor Surya Prakash from IIT Hyderabad, who will be delivering his keynote talk on corrosion-free fiber-reinforced polymer reinforcing bars for concrete structures. Dr. Arunachalam will be delivering his talk on wind-induced lock-in effects on tall and circular structures. We have another industry keynote with us from Mr. Arpit Mehta from NPCIL India. He will be giving his talk on momentum for young civil engineers. We also have a keynote talk scheduled by Dr. Arnasis Chakrabarti from IIT Guwahati, and he'll be talking about Kalman filters and its advanced variants for condition assessments of civil infrastructure. We have the honor of having Professor Sandeep Singh delivering the talk from IIT Roorkee about vernacular heritage practices for earthquake resilient structures in Himalayan region. Professor Sandeep Singh from IIT Science and Technology. Professor Souradeep Gupta from IISC will be delivering his talk on investigations of biochars from biomass waste as a carbon sequencing and mixtures in cement-based building materials. And Dr. Gang from NUS again will giving the talk on structure and property of alkali silica reaction products, recent evidence from synchrotron radiation. Now, without further ado, I'd like to invite our chief guest, Dr. Konkyan Howe, for his welcome address as a chief guest for the event. So I'll just give a brief about Dr. Kong. He is currently a senior lecturer with the Department of Civil Engineering and Environmental Engineering at National University of Singapore. He graduated with a bachelor's degree with first-class honors and a PhD in civil engineering from NUS as of 1999 and 2004. He completed his MSc in Advanced Reinforced Concrete Design, Advanced Pre-stressed Concrete Design, Advanced Structural Steel Design, and Dynamic Analysis of Earthquake Design of Buildings with an overall cap of 4.75 out of 5, and was awarded the NUS President Graduate Fellowship in 2002. His PhD focuses on the area of structural seismic engineering and advanced finite element modeling and analysis. Since 2005, Dr. Kong is also practicing qualified engineer who specializes in building and infrastructure projects, including bridges. He is a chartered engineer and international professional engineer with 13 years of experience as a consultant for many construction projects in Singapore and overseas. In his postdoctoral studies and acting principal investigators related to advanced concrete technology of Singapore government funded by R&D projects, Dr. Kong has also researched on areas of high-strength, lightweight concrete, high-performance oil-well cements, self-healing, and sustainable concretes as repair materials. He is currently serving as a technical committee member of the Civil and Structural Engineering Division of the Institute of Engineers, Singapore. He is serving as a working group technical member on SSEN 1376670, Execution of Concrete Structures Code, listed as a technical expert witness with the Intellectual Property Office of Singapore, serving as a senior member in RILAM's Technical Committee 273 RAC on structural behavior and innovation of recycled aggregate concrete, and serving in ASTM Technical Committee C09 on concrete and concrete aggregates. As a researcher and practitioner with combined background of concrete technology and structural engineering, Dr. Kong is diligent and passionate to create innovative, sustainable concrete and greener structural engineering solutions which can benefit the whole community. So we'll like to invite Dr. Kong to address us. Dr. Kong, to you.
Yes. A very good morning to distinguished guests, the organizing committee, patron, Professor Dr. Rajendra Kumar Sharma, Professor Dr. Vinod Kumar, and conference, this Professor Dr. Ashok Kumar Gupta, Professor Dr. Ashish Kumar, and also friend, conference chair, Dr. Gupta. I'd like to express my this honor and also thankfulness to have a opportunity to have a dialogue session and also to share knowledge, right, in this area, in this very good international conference on structures, materials, and construction 2021, organized by the Civil Engineering Department of JUIT. Yeah, I'm also very, very happy that some of our published documents also will be published in the Scopus Index Springer Book series under Lecture Notes in Civil Engineering. And with that, I'm happy and grateful that we have also the very good support from partner institutes, from the Atria Institute of Technology, the Indian Geotechnical Society Shimla chapter, the Institute of Civil Engineers of India, the Institute of Engineers Shimla chapter, and the Indian Green Building Council Chandigarh chapter. And I hope to visit your university next time in Himra Pradesh. Yeah. Okay. Yeah. And yeah. So yeah, that's the just a thank you notes. Yeah.
Thank you so much, sir. Thank you so much. So sweet of you to express your desire to come to us.
Yes.
We'll be having really a wonderful session with you if you are here in India anytime.
Sure.
You can please call us.
Yeah.
So thank you once again for your kind words and opening and giving a welcoming remark for the conference.
Yes.
Now I'd like to invite our Vice Chancellor, Professor Dr. Rajendra Kumar Sharma. He has a vast teaching experience of more than 20 years and has recently joined as Vice Chancellors at JP University of Information Technology, prior to which he was appointed at Thapar Institute of Engineering and Technology, Patiala, Punjab, in various positions, including Dean of Faculty Affairs, Dean of Academic Affairs, Head of Center of Information Technology and Management, Head of Computer Center, Head of School of Mathematics and Computer Applications, and Head of Department of Computer Science and Engineering. He is a distinguished alumnus of IIT Roorkee and completed his MSc in Applied Mathematics, MPhil in Computer Applications, and PhD in Mathematics from there. Sir is an inspiration to all with his dynamism. He has already won so many hearts at JUIT. We would like to invite Honorable Vice Chancellor, sir, to the virtual podium to address the conference. To you, sir.
Am I audible?
Yes, sir.
Okay, thank you, Tanmay. Thank you so very much for kind words. I know probably Jeet Kumar Gupta ji will be with me here if I say that please don't call me honorable. I'm requesting this third time in a conference. Gupta ji, I have requested them. There is nothing like honorable kind of a thing in a dictionary for human beings. I say that this word be used for only God. Krishna, Shiva, Ganesha, please. I am requesting this third time. Don't do this. Please spread this message. But anyways, thank you so much for your kind words of introduction. Yes, I have been at various positions in Thapar Institute, and I have been given this responsibility here at JUIT. Yes, I'm probably the youngest faculty member here. I call myself this way, that I'm youngest faculty member, unless someone else joins. Okay. So a very good morning to you all, Professor Kong, Professor Gupta, and others who are present here in this session. I have seen here there are 129 participants. This is a very good number. I'm very happy to note this. I welcome you all to this inaugural session of this International Conference on Structures, Materials and Constructions 2021, hosted by the Department of Civil Engineering of my university here. I'll give you one very brief idea about JUIT. First, Professor Kong, as you mentioned that you have never been here to this place, so you'll have to travel to Chandigarh
Okay.
by air, and then we will pick you up from Chandigarh airport, and this is around 2.5 hours journey from Chandigarh airport.
Okay.
And then you might be knowing that this Himachal Pradesh is having a very green cover, very green cover. So you might be listening these days the news about New Delhi, that the air quality is very different there. But that is not the case here in this particular area, in this region. The air quality is good. I mean, you can always check that using Google.
Okay.
Google information. So for that matter, I mean, this is a very different place. I mean, and after joining this place, I came to see when I came here. So I also did not see this university before joining, and I was we really surprised by the construction, by the things that they have done here. I'm really impressed. I mean, in my earlier university, Thapar Institute, they have also done very great constructions, but this kind of a construction in 2002, this is actually really appreciable. So I'm sure that the delegates, Professor Kong or anybody else who is interested and who wants to come here, he will find this a different place.
Yeah.
And my civil engineering department is the old department here, started with the university itself. And this is also one point that the promoters of this university, they are also there in the business of construction. So that's why I feel that they have actually invested a lot here in constructing this kind of a place in hills. I mean, you will not find these kind of places in India. I mean, these kind of universities in India. But having said that, I mean, probably constructing the buildings and having these kind of things is not that important. The important thing is this, that we have a very good organic component of the university, which probably the young team and all team here, including Tanmay Gupta, Ashish, and other senior faculty members, junior faculty members, will help me in building, in taking this to different heights in the coming years. So the organic component, so I believe every one of us can actually contribute one's own bit in actually increasing the quality of the air, quality of life around you, I believe. So for example, when I joined this place, I was given one printer which was not having duplex printing, Ashish. So what I did, I asked them to change my printer. And I have given this verdict to hear that no printer should be purchased which is not having automatic duplex printing. So what I'm trying to say, I mean, this is not a great thing. I mean, this is a very small thing. But what I'm trying to convey is this, that each one of us, if we do bit by bit, probably we can have a better environment around us. I believe this is my feeling here. And I also mentioned this in the last conference. I mean, whatsoever we do in our lives and in construction or at any place, whatsoever you are doing, you must consider the nature, that what will be the harm to the nature by this act of mine. So I discussed this. I mean, they are building highways and all in India these days. So they should try to find some ways and means so that, I mean, this is also true for a country of the size of India. This is required that we need to build things. But in those processes of building the things, how can we minimize the impact on the nature? So we should keep on thinking this in our mind, that how can I minimize, how can I reduce the impact on the nature? So that, I mean, we give a better place for our generations to live. Otherwise, they will fight with each other. They will have a very different place. And I'm also sure that with a little knowledge about the theme of the conference. I'm Professor Kong. I did my education as mentioned in maths, but I switched myself to computer science area. So I'm not that expert in this area where the conference is being held, but I know that there are advances, there are things that are being done by scientists to actually include the wastes in order to build, say, roads, build the buildings and all. I know that in Delhi there was a project wherein they took the waste material of polythene bags in order to build roads. Am I correct, Tanmay?
Yes,
Okay.
correct.
So I mean, so these kind of innovations are required for our country, for this country at least. That I mean, there's a lot of waste being generated. How can we better utilize that? Right. So we should also think in those directions. I know that, I mean, the theme of this conference and the developments in civil engineering itself are going in that direction. But yes, thoughts do not have limits. I mean, we can think very, very different things in our lives. Okay, so probably I'm sure that the faculty in the Department of Civil Engineering has these ideas in their mind, you know, when they thought of starting the activities related with this conference, that okay, we should bring the like-minded people together, and then probably we should deliberate, discuss the things so that we can come up with some ideas, some new ideas, and which can see the light of the day in future. They are daily implemented at some place. Okay, I'm sure the deliberations in this conference will really be very, very innovative, very, very thoughtful, and each one of the participants will have some or the other benefit from this conference, in terms of publication, in terms of ideas, or anything else. Okay, so with these few words, I would like to have a very, very special. I will convey a very, very special thank you to our chief guest, Professor Kong, National University of Singapore. Thank you for joining, Professor Kong, and helping to organize this particular conference. I'm also thankful to SL Swamiji, Chairman ICE India, Dr. T.N. Srinivasan, Principal Atria Institute of Technology, Bangalore, Engineer Pankaj Dadwal, Chairman Institution of Engineers India, Shimla Chapter, Ajit Kumar Gupta ji, Chairman IGBC Chandigarh Chapter, our own Professor Ashok Gupta, who is working as Dean Academic and Research with us, Professor Ashish Kumar, and of course Tanmay for organizing this. And also I know that these kind of efforts need a number of persons coming together and then working on this. So I'm also thankful to all the organizers here who have contributed in one way or the other. And also thank you the collaborating partners for the organization of this particular conference. I'm sure we might be having some sponsorship also, Tanmay. Thank you for all the sponsors as well. And I'm sure my Department of Civil Engineering here will keep on organizing such events where the like-minded people come together and then they discuss and deliberate. I had one request when Tanmay came to my office and told me that you please join, that I have to join here in this particular session, that we should even reduce the number of papers. So we have 100 papers. No, you bring that to 60, 70 in next conference. So conferences are also known from the quality of publications, and I'm sure that quality is there when you are having less numbers. So you have this kind of a conference next time, that okay, so this conference is known in the world that they publish very interesting papers. You have that particular idea. Okay, with these words, I again thank you all. Thank you, Professor Kong, once again. And wish you all the very best and very, very interesting discussions. Thank you so very much.
Thank you very much, sir. Thank you. Thank you very much, sir, for your kind words and your experiences which you have shared with us in this few days. Next, now I would like to invite Dr. S.L. Swami, the chairman of the Institution of Civil Engineers India. He is the founder chairman and he is a visionary. He thinks far ahead of present and imprints his vision, which is seen in his growth of the industry and nationally and internationally. He's a dynamic leader and a role model for others to follow. These words, I like to invite the chairman, ICE India, Dr. S.L. Swami. Over to you, sir.
Good morning. Good morning to you all. Professor Kong, Chief Guest of today's event, Professor Rajendra Gupta, Vice Chancellor, JP University, distinguished speakers at the today's conference from India and abroad, delegates, ladies and gentlemen. You are all aware that we have passed through the challenging time which this planet has ever seen. A lot has changed around us globally. The pandemic has impacted every sphere of human activity, but nonetheless, it has given us the opportunity to make optimum use of the power and effectiveness of technology-enabled learning. Probably, there could not have been more appropriate opportunity which could have challenged or changed the game of learning to enter the new normal and more spirit and passion. We at IC India feel happy to associate ourselves with ICSMC 2021, an international conference on structural, material and construction 2021, being organized by the Department of Civil Engineering, JP University of Information Technology, Himachal Pradesh. The primary objective of this international conference is to create a forum of practitioners to meet the global leaders in the field of structural design, construction, and materials. The construction industry is upgrading technology to make construction management and site operations more efficient and sustainable. The major construction industry trends included building information modeling, construction robotics, and the use of advanced building materials. Further, the COVID-19 pandemic creates the need for newer ways of construction that adhere to worker safety and regulations. Hence, startups and scale-ups increasingly develop innovations around prefabrication, work safety, and construction robotics. Parallelly, 3D printing and green building solutions significantly reduce the negative impact of construction on environment. A famous quote says, engineering is a profession, art of applying science to the optimum conservation of natural resources to the benefit of man. This quote confirms the influencing role of engineering in the development of nation. Engineers are those who operate interface between science and society. Engineers are the backbone of development and technology. When such is canvassed, civil engineers have to play significant role so that India feels proud to provide world-class infrastructure. How could it will be possible? Our learned expert speakers on the subject will throw light on it and enlighten us about the ways and means of innovations in structural design, new construction materials, and construction techniques. IC India, ever since its inception, has focused on the mandate given to it to contribute in the furtherance of civil engineering in order to actualize its mission to promote and strengthen civil engineering. I'm delighted to share with you all at this proud moment that ICE India is the member of Asian Civil Engineering Coordinating Council, representing our country, which has 15 member countries as its members, namely US, Australia, India, Pakistan, Korea, Nepal, Vietnam, Taiwan, Indonesia, Bangladesh, Japan, Mongolia, Philippines, Myanmar, and Russia. To achieve its objectives, an international conference called the Civil Engineering Conference in the Asian region, and shortly it's known as CECAR, is held once in every 3 years as one of the main activities of ASEC. So far, 8 CECARs have taken place at Manila in Philippines, Tokyo in Japan, Seoul, Taipei in Taiwan, Sydney in Australia, Jakarta, Indonesia, and Honolulu, USA. The Asian Civil Engineering Coordinating Council, in its 24th executive meeting, held in April 12-14, 2018 at Hanoi in Vietnam, has decided that upcoming 9th CECAR will be hosted in India by the Institution of Civil Engineers India in 2022. The upcoming international conference, CECAR 9, is being held in India for first time at Goa on 21st to 23rd September 2022 with the core theme of sustainable design and eco-technologies for infrastructure. CECAR brings together academicians, professionals, policy experts, and thought leaders, industry leaders, and governments every 3 years to share ideas and develop their professional skills and expertise. The event will unite nearly 800 professionals from over 15 countries to discuss the latest innovations, new strategies, and best practices. It will also have the exclusive expo hall, which would highlight the diverse and innovative programs, products, and service advancing the future of civil engineering. Keeping the scale and impact of this conference in view, the various ministries of Government of India, like Ministry of Ports, Shipping and Waterways, Ministry of Mines, Ministry of Jal Shakti, Ministry of Road Transport and Highways, Ministry of Science and Technology, Ministry of Housing and Urban Affairs, Ministry of Defense, National Technology Center for Ports, Waterways and Coasts, IIT Madras, and NITI Aayog, DRDO, etc., are already on board with us as knowledge partners. I take this opportunity to invite all to log on to the dedicated website of ICE for this particular event, www.cecar9.com. I am very happy to associate myself at the inaugural ceremony, and I wish all the success of this conference, and I am sure you all will be greatly benefited with the outcome of this conference. My best wishes to all of you. Thank you.
Thank you so much. Thank you so much, Swami sir, for your kind words and for the event which is upcoming, CECAR 9. Now I'll request our next distinguished speaker, the Chairman, IGBC Chapter Chandigarh, Mr. Architect Jeet Kumar Gupta ji, to share a few words with us. Jeet Kumar Gupta ji, he has an experience spanning over 50 years in architecture, urban planning, development, management, planning, legislations, policy planning, and architectural education. He is a pioneer and a very well-wisher of this institute. We have just opened a student chapter with IGBC few months back, and we have been waiting to listen from Mr. Jeet Kumar Gupta. Over to you, Jeet Kumar sir.
Thank you, Tanmayji, and thank you for the opportunity. Let me, first of all, on behalf of the IGBC, thank JP University in general, Vice Chancellor Professor R.K. Sharma ji in particular, the chief guest of the morning, Konkyan from Singapore, and my learned colleagues. It's both an honor and pleasure to be part of this great meet. That's an international conference on material, structure, and construction, which is dedicated to a very important cause, and thus promoting qualitative structure, etc. Theme of the conference remains highly relevant in the context of rapidly increasing population, massive urbanization, globalization and liberalization of the economies, with India trying to become a 5 trillion economy by the year 2025. As per projections made by global agencies, India is going to be the largest populated country in the world by the year 2036. When nation will have a population of 1.5 billion, we are projected to go beyond 1.6 billion by the year 2050. Half of India will be living in urban areas. That means we'll be adding another urban India in the next 30 years, with population rising from 37 crore to around 800 million people. I think challenges are enormous. Projection made by McKinsey Global Institute with regard to India awakening, and they are looking at the urban context by the year 2030. It says India will need annually an addition of buildings to the tune of 700 to 900 million square meter every year. They have to create 350 kilometers of metros, 1.2 billion square meter of road space, and that is the an investment of $1.2 trillion every year to meet these demand of infrastructure. Such an enormous construction has implication in terms of resources, energy, water, waste, material, and technology. We know buildings are the largest consumer of energy, resources, and generator of waste. They are also polluter of environment and ecology. Accordingly, buildings have to be planned with care and caution. They have to be designed in such a manner that they don't adversely impact the environment and ecology. They don't deplete the nation of the resources. They are not antithesis to the environment and ecology. They remain supportive to the, the total context of the built environment. In this context, I would like to remind our learned listener and the faculty that IGBC is trying to do its best to make this world more sustainable and livable. IGBC is trying to promote the concept of green building, and now we are working on the zero energy. So net zero is going to be the next target. And you have seen, Conference of Nations, which is heading in the year in the Glasgow by 2036. They are debating the issue of the global sustainability. And I think role of civil engineer, the architects become very, very crucial, because building will be the one which will be determinant of the total sustainability of the world. And let me also tell you, if civil engineer, the architect fail, I think world will be in a very, very bad position, and world will never be able to achieve the 17 sustainable goals, which have been enunciated by UNO to make this world sustainable. With more than 7.9 billion square meter of space already as declared as a green footprints, IGBC is trying to make India global leader in the domain of green building, and also making available the sustainable building within the reach of each and everybody. It should not be cost intensive, it should be cost effective, Looking at the entire context, the challenge before the building industry are going to be enormous. We need large amount of building material for construction. These material have to be sourced in such a manner that they do not adversely impact the environment. Materials which we are trying to make, they should be made from the waste generated by both industries and agriculture. We have to work on a circular economy so that the waste which is available in the city is converted into a wealth for the construction of it. And then we have to reinvent the materials which are lasting long, which have minimum implication of energy being making them, that is embodied energy, and they should also be, lightweight. They should require minimum maintenance, and they should be able to be, sourced quickly without impacting the environment. And that what will be, that even after the building is demolished, we need those materials to be reused in the next building. I think structure and construction have to be such that the buildings have to be lightweight, lean and smart, capable of withstanding all disasters, both man-made and nature. And they have to be built in the most cost-effective manner and in a time-efficient manner, and having the best of the quality, and which are, impacting the environment ecology in the minimum manner. I think we have to change the manner in we are doing the construction. I think construction have to move from the construction to manufacturing. The building have to move from the, they have to graduate now from the construction to manufacturing, from on-site to off-site, Considering the amount of, buildings required, I think we have to reinvent the industry, of construction, and we have to make sure the buildings are available in the shortest possible time, of the best quality, in the most cost-effective manner, and without adversely impacting the environment and ecology. We have to look at the people, in India, 17% of people living in slums, So cost-effective housing and building remain one of the most contextual and relevant. I know building industry is under a
I guess there is some technical issue with Sir's connection right now.
Is audio lost?
Yes. We are very sorry for his loss in the connection. So moving ahead in the program, next our partner institute, we like to invite from Atria Institute of Technology, Dr. T.N. Srinivas, who is the principal of AIT Bangalore. He is a dynamic professional with a rich experience of 31 years in academics, administrative and research domain in technical education. He is seen often on his DD Chandra network on Doordarshan Bengaluru, Kasturi Network, Janashri, Udaya News, TV9 Kannada, News 9, Sri Shankar TV, and Praja, and among others, giving several live technical educational programs. So not taking much time, invite to address the conference Dr. T. N. Srinivas, Principal AIT Bangalore.
Thank you. Can you able to hear me?
Yes, sir.
Yeah. Good morning. At
Your
the
video
outset,
was,
yeah. Can you able to hear me?
yes, sir, we are able to hear you.
Yeah. So, good morning. First of all, it's a great opportunity you have given to Atria Institute of Technology to a part of the ICSMC conference. Particularly, I'm grateful to the Dr. Tanmay Gupta ji, as well the distinguished chief guest for the day, Dr. Kong, and the special thanks to the Vice Chancellor of JUIT, Professor Rajendra Kumar Sharma ji, and especially I would like to thank all the conference team of ICMC having given us the opportunity as a part of this conference. So at the outset, this really I represent from the beautiful city of Karnataka, Bangalore. It's an opportunity, place of opportunities we call here. Whatever in the world happening, which you can find in Bangalore, as you all aware of it. My institution is at the heart of the city of the Bangalore. We run undergraduate, postgraduate, as well as all the research centers as well. In our institute, civil engineering is doing extremely good. But the challenge for the civil engineering, as you all aware of it, the civil and mechanical has taken slowly the backseat in the engineering admission is concerned throughout the, I think in India, it's been observed. I think this kind of conferences will bring, overcome this, you are going to attract the top notch of the brainies into this core engineering. We call it civil and mechanical. Probably the civil is the place. Without the civil engineering, we can't live. You know that. Without mechanical, we can't live. That's what we say. It's a core engineering. I think this kind of the conferences will enlighten the people in and around us. So to be a part of this, I really appreciate having given an opportunity, Atria Institute of Technology, as a partner institute in this great conference. All these deliberations, I think a lot of brainstorming, it happens. So I wish it will be wonderful, the conference proceedings which we are going to see the end of the day. Once again, thank you so much for all the organizing committee for having given an opportunity for the Atria Institute of Technology. And particularly, I have the special thing to Himachal Pradesh in Joginder Nagar. I think one of my known friends has lived in, and I visited the Himachal Pradesh, one of the beautiful state it is. I think the wonderful place you are organizing. I wish the deliberation should go in a very big way. Thank you. Thank you once again to all the people who are present in the conference. Thank you.
Thank you so much, sir. Thank you so much for your words of kind appreciation and your enthusiasm for the event. We are very sorry, Architect Jeet Kumar Gupta ji, we lost you in between, so we move ahead with the program.
So, can
Sir,
I talk? Sorry.
You we had to move in that way. We are
Okay, I know.
sorry. So, can we go ahead? Shall we go ahead with the program?
I can complete?
Yes, sir, please, sir.
Thank you very much. I was trying to tell you, I think construction industry now has a lot of challenges. We have to reinvent the construction industry. Rather from construction, we have to go to manufacturing. So therefore, from on-site, we have to take it off-site. We have the distinct advantages the off-site construction has. India, with the kind of challenges it has in the construction industry, which I have enunciated, I think the normal system will not do good. So we have to do differently. We have to do distinctly. We have to do innovatively. We have to reinvent our structure. We have to reinvent our material. We have to reinvent our technology to redefine the construction industry. And that will be, I think, the greatest contribution of the civil engineering and the architecture to this world. And in fact, I was trying to communicate that This world can never be sustainable without an architect and engineer working their own professional work. No, because we know the context of building. Half of the energy is consumed by building. How 1/4 of the water goes into making a building, and so is the 1/3 of the total carbon emission are attributed to the way the buildings are constructed. 1/3 of the people which are visiting hospital are suffering from the sick building syndrome for the simple reason the way the buildings are being planned and designed. So I think we have to make building more supportive and promoter of environment and ecology. And that's what, we will be all looking forward in this conference, with new material coming in, with new technology coming in, and with the new structure defining the built environment itself. I would wish, had you included the design, only one component, design, this conference would have been holistic. Then you are looking at the entire context of the building, right from the cradle to, I would say, the grave itself. That building, the holistic looking, and the things would have been different. But I'm going to conclude and finish it, with this remarks that we should now ask each and every unit, like JP University, the pioneer in the civil engineering, and JPs are known for their wonderful work in the area of civil engineering and the dam making. I think your university should have one of the finest lab, looking at the structure, looking at the material, looking at the construction. World is doing innovation, and I think these are patented things which needs to be done at the level of the academia. Maybe you are already having the support of JPs, who are in the this profession itself. Jointly, it can be done. New material needs to be invented. India needs new technology. We don't need to copy from outside. We have our own material, we have our own context, and we have our own kind of climate, which is different. A building in Himachal will be different from what is being done in the Jaipur or in the Red Desert. So therefore, I think in hill areas which are being prone to a lot of unauthorized and substandard construction, and there are a lot of disasters we see happening in the cities like Shimla, etc. Let JP University and the Civil Engineering Department come forward with an innovation in structure, the kind of building and the kind of material and the technology that could make this world very sustainable, and we head towards zero and attain the SDGs goal of 17 goals, and IGBC will be at your support, will be a partner in this to make sure that building remain not a deterrent to the environment, but a supportive and promoting the best quality of life. Thank you. Thank you very much for giving me the opportunity and for, this disconnect. I'm sorry for this. And thank you. Thank you. And I wish you all the best.
Thank you so much. So kind of you, sir, to continue and deliver your address and enlighten us the importance of sustainability and what pioneer work IGBC is doing and inviting us in the same journey. With this, I'd like to invite the next guest, the chairman, Indian Engineering Institute of Shimla chapter, Engineer Pankaj Dadwal. He is an eminent electrical engineer, having joined Himachal Pradesh State Electricity Board, now HPSEBL, in 1986 as an assistant engineer. He has served HPSEBL at different positions and presently having the organization as managing director. Having long association with IEI India and remained honorary secretary, he has from HP State Center with effect from 28/12/2013 to 9/12/2015. As of now, he is chairman IEI HP State with effect from 31/1/2019 till date. Due to his busy schedule, Engineer Pankaj Dadwal is not here currently with us. We will request Mr. Subhash Chandra Gupta, the committee member of IEI Shimla, to please address us on his behalf. Subhash Chandra ji, if you are here. Mr. Subhash Gupta ji. Subhash Gupta ji, are you able to hear us? Subhashi, your mic is off. Subhashi, if you can hear us. Your sound is coming in bits and pieces. I guess there is a technical limitation to it. In case if it works out, we'll move ahead with this. Till then, yes, Subhashi.
Yes.
We are able to hear you in bits and pieces. Your mic is cracking, so keeping on for a whole long time. Somehow this is the limitation we face in virtual conferences. Sorry for the same. I hope he will be able to join us in some time and deliver the address from Engineer Pankaj Tedwal. So moving ahead further, the last and not the least, our last partner institute is Indian Geotechnical Society, Shimla chapter. Its chairman is Professor Ashok Kumar Gupta, who is also Dean Academics and Research at JUIT. Sir is also not with us today. On his behalf, Mr. Neeraj Singh Parihar, Secretary of IGS, will address us. To you, Mr. Neeraj.
Thank you, Dr. Tanmay, for giving a chance to speak out here. Respected Vice Chancellor Sir, JUIT, Professor R.K. Sharma ji, our Chief Guest, Dr. Kong, Engineer Sir Swami ji, the Chairman of ICE India, Ajit Gupta ji, Chairman of IGBC Chandigarh, Dr. T.N. Srinivasa, Principal, AIT Bangalore, Engineer Pankaj Dadwal ji from IISC Shimla chapter, and HOD of the Civil Engineering Department, General Chair, Professor Ashish Kumar, Dr. Tanmay, and our keynote speakers of the day. A very good morning to all the dignitaries and the participants present here. So on the behalf of IGS Shimla chapter, I welcome you all to the very stage of this event, first International Conference on Structures, Materials and Construction. And as Secretary of IGS Shimla chapter and also the member of this organization, JUIT Waknaghat, I would first of all like to extend my sincere gratitude to our collaborating organizations who contributed positively in the conduction of this event. Just giving a brief about this IGS Shimla chapter. This chapter of IGS was founded in the year 2011 under the chairmanship of Professor Ashok Kumar Gupta, who is the current chairman also, and is continuing the services for the society. And since its inception, we have hosted a number of technical events, including international conferences, workshops, webinar series for the benefit of the entire geotechnical community. However, I should say, luckily, this is the second time within a year that we are collaborating for a multidisciplinary event, and it's a pleasure to host the participants from various backgrounds of civil engineering. Not needed to say that we had a very rough phase of COVID-19 pandemic in the past 2 years, but it is also a blessing in disguise, we can say, that we as academicians and practitioners have learned to adapt to the situation. And even these toughest times have not stopped us from sharing the knowledge, ideas, and expertise among the civil engineering community. And obviously, the events such as like this have played a big role in continuing the advancements and circulation of new ideas in the civil engineering field. And as the previous speakers did mention, the human development have enormous challenges. But obviously, the challenges comes with opportunities also. So there are various challenges like effectiveness of resource utilization, sustainability, and we all have a huge responsibility over us to answer them combiningly as an engineering community. With this note, I would like to thank our expert speakers who derived the time out of their busy schedule to share the knowledge and experience with us, and also congratulate the participants who will be presenting their research work in the technical sessions to follow. I strongly believe that the sessions to come in these 2 days will be a guiding light to the entire community, and all of us will be benefited in a way or the other. Lastly, I would extend my greetings to Dr. Tanmay Gupta as well, and all the associate reviewers who have worked tirelessly for last few months to make the event of this magnitude smoothly happen. So I wish a very good luck to the organizing committee and all the participants. Thank you.
Thank you. Thank you so much, Mr. Neeraj, for introducing IGS on our behalf. So Bhaji, if you have connected back with us.
Yes.
Yes, you can please go ahead and.
Yes. Good morning. Chairman was preoccupied, so I am this civil chapter from Shimla. I am executive member of that. And if you're getting my sound, should I start now?
Yes, Bhaji, please.
Okay. Sir, the Institution of Engineers, we call it IEI, is a statutory body to promote and advance the engineering and technology established in 1920 and incorporated by Royal Chapter in 1935. It is the largest multidisciplinary professional body of engineers encompassing 15 engineering disciplines with a membership of more than 820,000 and serving the nation for more than 9 decades. The IEI has headquarters located in Kolkata with national presence through more than 100 centers and several overseas chapters, forums and origin. The institution was granted Royal Chapter in 1935, as I said earlier, by Majesty Emperor George V, which was a momentous event in the annals of engineering industry and education in India. The Royal Chapter endowed the institution with the responsibility to promote the general advancement of engineering amongst members and persons attached to the institution. IEI has been recognized as a scientific and industrial research organization by the Ministry of Science and Technology, Government of India, and besides conducting its own research, provides granting aid to undergraduate, graduate, postgraduate, and PhD students of engineering institutes and universities. The Institution of Engineers is the first professional body to represent India in several international bodies such as the World Mining Congress, the World Federation of Engineering Organizations, and so on. The Federation International du Baton and the Federation of Engineering Institutions of South and Central Asia. It also has bilateral agreement with a number of professional societies across the globe. So it's more or less a globe institution. IEI holds the International Professional Engineers Register for India under the Global International Professional Engineers Alliance. The institution also awards the Professional Engineers Certification. The Institution of Engineers is a pioneer body to introduce, starting from 1928, continuing engineering education program, successful completion of which is recognized as equivalent to the degree in engineering by the Government of India. The Union Public Service Commission, the state government, and many public-private sector organizations in the country. The Institution of Engineers, with its headquarters in Kolkata, India, is administered by a national council with the president of IE as its head. Ever since its inception, IEI has been the forerunner in setting up national standards for promoting the country's industrial base, which culminated on the formation of Indian Standard Institution, now called the Bureau of Indian Standard. IEI, in collaboration with the Springer, regularly publishes peer-reviewed international journal in 5 series covering 15 engineering disciplines. HP State Center Shimla, since its inception as sub-center in year 1974. I'm not very old, but this thing, upgradation to local center in 1983 and full-fledged center in 1988. Great and untiring source of reversed Brother engineers have continuously nourished and taken care of mission objectives and the goals of this great institution of engineers at the center. In pursuit during 2013, a Center for Skill Development and Engineering Consultancy has also been established under the aegis of Institution of Engineers, HP State Center, to shoulder the added responsibilities of quality training, capacity building, skill development, and consultancy services in the technology knowledge domains. Here we may make indefatigable efforts to search and engage best of faculty for our trainees. The Guru Dronacharya made Arjuna conquerable in the world. Likewise, well-known experts, faculty trained at CESDEC, as we call in short, to make the trainees the best in their respective field of operation and the brand IEI flying. It is a matter of great pride that this CESDEC has been upgraded to the National Skill Development Forum pursuant to a resolution of the Council of Institution of India adopted in 700th meeting held in March 31 April 2018 at Hyderabad. The NSDF shall have powers to all matters and things in fulfillment of its objectives. Under the general guidance of the said council, NSDF shall play a very active role in the area of skill enhancement, capacity building, quality training in emerging, evolving, cutting-edge technologies, and where much has not been published or practiced for professional engineers, managers, scientists, and young graduates. Beside NSDF shall undertake consultancy services in technology management domain, shall have formalized structure for the cohesive synergistic efforts in the domain of skill development in IEI. Despite being a small state, this center has now become an example to the emulated by other state centers due to its beautiful infrastructure, numerous professional activities round the calendar, hosting various programs given from the IEI headquarters from Calcutta, and the training program in consonance with the training calendar of ESCI Hyderabad. This all has become possible only due to enormous cooperation of the corporate members attached to the state center and its dedicated team of executive committee members who are bestowed by the state center. Thank you very much. Thank you.
Thank you so much, Subhashji, for your kind words and telling about the HPIEI Shimla chapter.
Yes.
Now, lastly, I'll move to our professor and head of Civil Engineering Department, Professor Ashish Kumar Gupta. Professor Ashish Kumar, who is also the Principal General Chair for ICSMC 2021. He is a member, he is having membership of various technical societies, including Associate Member of Institution of Engineers, India, Life Membership of Indian Water Resource Society, Indian Society for Hydraulics, India and Indian Geotechnical Society, IGS. Having more than 17 years of teaching and research experience, he is currently heading the department. We'd like him to say a few words.
Thank you, Tanmay. Respected Vice Chancellor, Sir, Professor Rajendra Kumar Sharma ji, we are thankful to you, sir, for gracing the event with your presence. Our chief guest of the event, Dr. Konkyan Howe from the National University of Singapore. We are thankful to you, sir, for accepting the invitation as a chief guest for this conference. Engineer S.R. Swamiji, Chairman of Institution of Civil Engineers, ICE India. Architect JUIT Kumar Gupta ji, Chairman of IGBC Chandigarh Chapter. Dr. TNC Srinivasa ji, Principal of AIT Bangalore College. Engineer Pankaj Dadwal ji, Chairman of Institute. My faculty colleagues, our keynote speakers of the conference, various participants from the different academic institutions and organizations, and ladies and gentlemen, a very good morning to all of you. On behalf of Department of Civil Engineering, I welcome all of you in this first international conference on structures, material and construction. So this basically conference is being organized by Department of Civil Engineering with the support of our partner institutions, that is our ICE, IGBC, Institution of Engineers Shimla chapters, IGS, Himachal Pradesh chapter, and AIT. So we are thankful to our partner institutions that they have provided continuous and constant supports in order to organize this event. So the conference is basically intended to provide exposure and share work amongst the civil engineering community about the new innovative practices and techniques applied in the field of construction. And basic objective is to create a sustainable environment. So that is the main focus, that how what our different keynote speakers who are talking about different technologies which is now emerging in the field of civil engineering, our different participants. So I think that all we will be focusing on the sustainable environment. So today we all know that infrastructure is essential for the development of any nation. As Kumar Gupta ji also said that India is a huge country and we are having a large community, we are large mass. So we need to develop our society in a big manner, and in that way we need to construct a number of buildings, a number of structures for various purposes. But what we know that this basically comes at a price, and that price is what we say that so somehow we are disturbing our ecology, we are disturbing our environment. So all of us being a civil engineer, we must keep in our mind that we have to somehow care about our environment also. We have to minimize the losses which is being which we are creating, or how we are disturbing that environment. So how we can do this? So basically we have to induct some innovative technologies, innovative ideas in our, either it is in the field of construction, either it is in the field of material, or it is in the field of methodology. So we all we all have to look in that aspect also, how we can apply the innovation, how we can apply the technology in the field of civil engineering. You know that if we talk about the field of automobiles, so they have very rapidly, they have captured the new inventions or new technology in their field of automobiles. You can see all that today the automobile industry is working on how they can minimize the emissions from the cars, from the automobiles. So in the same way, we have to do a lot of research. We have to induct the latest technology in our civil engineering methods, in civil engineering materials also. So all we know that today, if we do a collaborative research with some with the expert of the IT, or expert from the electronics field, or experts from the computer industry, then certainly and definitely we do some fruitful outcome, and that fruitful outcome which definitely give us output in terms of creating some sustainable development of our society. So what we need to do now, we need to apply some artificial intelligence, some machine learning, some IoT, and some drone technology, some blockchaining methods in our civil engineering in civil engineering field also. So what I request to our all participants and all of our researchers who are here present their ideas that they should work on development of the new advanced material. They should work on development of the new methods of constructions, and they should try to introduce latest technology, as I told you, like application of the AIA drone technology, either it is 3D printing or IoT or machine learning, use of machine learning. So we should incorporate all these technologies also, so that we can focus on the development of the sustainable environment. So that is my appeal to all our researchers, and in this conference all we have congregated to discuss and share our ideas, our research which is related to the construction material, methods of application, or either it is how we can minimize the effect of pollution which is being done due to that construction methods or processing of the materials. So that is all is the main theme of that our conferences, and it is my belief that we will be having a highly storming sessions, either it is from our keynote speakers and either it is from the participants who are going to delivering their research, and that will be beneficial to all of us. And with these words I will not take so much more time, and thanks to all of you once again for joining with us and gracing the occasion and gracing this conference with your presence. Over to you, Tanmay.
Thank you so much, sir, for your constant guidance and kind words to open this conference and welcoming all our guests. With this, we come to an end for the inaugural ceremony. We again thank our chief guest, Dr. Konkyan Howe, Engineer S.L. Swami, Dr. T.N. Srinivas, Engineer Pankaj Jadwal, Architect Jeet Kumar Gupta ji, Professor Ashok Kumar Gupta ji, Professor Ashish Kumar, all our wonderful audience, reviewers, and the participants. So now it's our time we are already running 15 minutes behind the schedule for Keynote 1, and Keynote 1 will be delivered by Dr. Konkyan Howe himself on chemical admixtures for autonomous healing in concrete, the past, the present, and the future. So we'll request the audience to please keep their microphone switched off during the keynote speech. You may type in your queries in the chat box of the Google Meet, which will be taken up at the end of the keynote. And authors having the presentations, starting in the technical sessions, which have already started due to the limitation of time. We are having a combination of keynote speeches and combination of technical sessions going on simultaneously. So in respective virtual classrooms, whosoever presentation is starting in technical sessions 1A to 1C, the parallel technical sessions going on, they may proceed there, and remaining participants are invited for Keynote 1 by Professor Kong. So I have already introduced, and we are already running behind of time. So I'll directly ask Dr. Kong to share his presentation and start with the Keynote 1. Dr. Kong?
Okay, yep. Thank you, Dr. Tame Gupta, distinguished guests. And so I'd like to share my presentation. I hope you can hear me.
Yes, sure.
Yeah. Okay, that's good. Okay. Dr. Tame, you can see the screen?
Yeah, the screen is proper.
Okay, can.
Thank you so much, sir. VC, sir.
Okay, yeah, great. Okay, a very good morning to distinguished guests, fellow academics, practitioners in the area of construction, and I've heard the speeches from the organizing committee and the institutions, and I'm actually very also touched and by the spirit of the diligence and the wanting to innovate for sustainable. Actually, and actually myself, I'm also a very passionate in the area of sustainable design, sustainable concrete, and I also believe strongly together with you all to create a better earth, to have use our engineering knowledge either in concrete material or civil and structural engineering to develop the sustainable future for the future generation. Okay, now with that, I would like to start with a keynote on the lecture on crystalline admixtures for autonomous healing in concrete, the past, present, and future. I'm the senior lecturer with the Department of Civil Engineering, and this is actually my email and my official biography. You can okay, from the Google Scholar. Okay, and is the presentation is with the International Conference on Structures, Materials, and Construction 2021, organized by JP University of Information Technology, India. The paper actually is also co-authored with my research fellow, Dr. Lai, on this very important and you can say it's a groundbreaking area in the area of healing, concrete healing. In our paper, we actually talk about the development of chemical admixtures for concrete use, which will be actually used for mainly to self-heal, particularly on the area of concrete durability, so as to have a longer structural service life. Okay, so one of the areas that we are actually dealing, we want to impart autonomous healing ability in concrete through the use of crystalline admixtures for repairing and sealing micro cracks in a structure. And this paper actually provides a comprehensive overview of the past and the current research on this autonomous healing using crystalline admixtures. And in my presentation, I may have put some background information for us to build up the knowledge. Yeah. Okay, so now basically we are talking about the area of self-healing, like healing the word. So when we're talking about concrete, and we know concrete is actually the most widely used construction material in the world, and actually one of the problems in concrete is actually the issue with concrete cracking. Okay, concrete cracking is actually as a background for participants also to build up the knowledge. So I hope that through this keynote lecture can also share with the audience to build up the fundamental background and also to create passion in the area of this research also, right? Yeah, so that's why I'm sharing some background. So now, cracking in a concrete actually is an inevitable phenomena which actually can take place when concrete actually in fresh state, okay, and also throughout a hardened state like a service life, due to various reasons like concrete shrinkage, weathering, loading, and so on and so forth. Actually, the presence of a concrete crack actually will actually facilitate transportation of fluid and gases into the concrete, potentially leading to the corrosion of the reinforcement in structural concrete. Reinforcement here can be the steel reinforcement, or it can be like pre-stress post-tension tendon or pre-tension tendon in structural concrete. So it can affect reinforced concrete and also pre-stressed concrete, thus affecting the integrity of the structural component itself. And we also know that actually one of the major causes of concrete degradation, the type of deterioration, majority of it, more than 85%, is due to corrosion in the steel, in the concrete itself. So when actually a concrete crack, that is not an issue. But when a reinforced concrete crack or when a pre-stressed concrete crack, that is an issue, because concrete actually is a composite material with steel. And in the building construction, we need to have a combination of both. So if it's just concrete cracking, that's not an issue. But now is the thing is that concrete cracks, it leads to the transportation of fluid and gases in the concrete, and causes the steel corrosion. That becomes an issue. Of course, other reasons being alkali aggregate reaction, frost, and so on and so forth. So now the development of crack treating technology in the form of self-healing actually is important. As current research found, also practice found that actually repairing and maintenance of concrete can be actually cost and labor intensive. Okay, so we are trying to study in this area. Now, the research motivation in this area is that why are we going into this area to ask us? We know that actually in the current development in structures and infrastructures around the world, countries which are actually earlier developed than us, for example, places in the United States of America, Japan, and Western Europe, they are now actually facing an issue. Actually, this is a worldwide trend. It's called aging in structures and infrastructures. Okay, mainly in developed countries, industrialized countries. Okay, and earlier developed countries, especially when the structures are actually past the design serviceability limit life of 50 years. For example, if let's say structures are built in 1950s, now in 2002 they are about, some of them are 70 years, some are even like even built in 1960s or 70s. So now the issue with these structures is that they are still serving. They actually are facing durability issue. Okay, and so you can see some the recent news worldwide, some local collapse in some bridges and some buildings happened not because of seismic, not because of typhoon loading, not because of additional loading in terms of vehicular bridges or vehicular cars and so on, but actually mainly due to the concrete degradation. Okay, because of deteriorating structures. Okay, so then this also lead to an increase in the structure needing for repair. Okay, so in a sense, this poses a challenge to the world, and in a sense also poses a challenge that we as practitioners or academicians or researchers want to try to solve this thing. Okay, to have a more sustainable, because you see, if we want to, if the structures are degradation, if you can repair it, okay, I mean you can preserve the building rather than demolish the structures. Okay, so that's one area of sustainable. Now, also in the recent report from the US Army Corps of Engineers, now we know that the US Army Corps of Engineers maintain one of the largest inventories of concrete structures in the world. And in the recent report in the US Army Corps, that even after they repair, okay, more than 50% of the repairs performed by the Corps structures are performing satisfactory. Okay, about 25% in the repair is actually not functioning, maybe due to compatibility issue, some material performance, and so on and so forth. So actually, so that actually leads to our research motivation to try to solve it at the core level of the issue, which is actually solving the thing at its crack level, because all these things happen. Cracks leading to corrosion, cracks leading to ingress of chemicals and water, leading to concrete degradation. Okay, all this happens is due to presence of cracks. Okay, in a concrete, yeah, and yeah. So that's why we want to how to seal the crack. Okay, so based on, so that's why that brings us to the topic of called self-healing in concrete. I hope to build us some motivation behind that. And now, why, to ask us ourselves, why are we studying this aspect of self-healing? Okay, so now, based on the Rylam Technical Committee 221 report, self-healing in the concrete actually is defined as any process by which the material itself, okay, by its own, improve its own performance and recover its performance after an earlier action has been done to reduce its own performance. So it can auto repair by itself. Okay, so now, according to the technical committee report, there are two processes by which a concrete can so-called self-heal. Okay, one is called the autogenic process, one is called the autonomic process. Autogenic process is actually a self-healing process where the recovery process actually uses the material components that could otherwise also be present when not specifically designed for self-healing. What it means that they are actually using its own material. The concrete is using its own material that actually, when you cast a concrete, for example, when you cast a concrete, you actually have a cement, water, fine aggregate, and coarse aggregate. So autogenic self-healing, what it means that the concrete itself uses the cement material inside, the chemicals inside, to auto self-heal. Okay, either by creating some of the CSH component to so-called self-repair. That's called autogenic. Now, autonomic self-healing process. Okay, this is a process when it's called autonomic, is that when the recovery process actually uses the material components in the concrete that otherwise not found in the material. So what it means that we are adding something inside the concrete besides the cement, the OPC, besides water, besides the coarse aggregate, besides the fine aggregate, we are adding some other things inside the concrete to so-called let it undergo autonomic self-healing. Okay. So basically, just now, as mentioned earlier, so self-healing concrete, they are divided into two aspects: autogeneous and autonomous. So now, current research in the state-of-the-art review, as of even in the late 2020, have actually reviewed that there are several methods. Actually, the researchers all around the world, like including in very many parts in the Europe universities, they are doing a lot of intensive research in this area. They are using autogeneous self-healing to actually do involving using cementitious material, fibers, nanofillers, and some curing agents like lightweight aggregates and super absorbent plastimers, to actually enable the concrete to undergo its own self-heal by its own self. Then another aspects of autonomous, they are actually using electrode deposition technology, shape memory alloy, capsule technology, vascular technology, or even putting a microbe technology into the concrete itself to so-called enable to self-heal. Now, in our research, we actually reviewed this area, and we found on our NUS site, and which actually we are doing research, a potential research gap, okay, of using besides using capsule vascular, we're using a crystalline chemical admixtures, okay, in this area. And like for example, just to share with us some of the very good world-class review paper in this area, published by the University of Cambridge, okay, and UK universities in the year 2000 on the self-healing cement concrete composites for resilient infrastructure. In this paper published in the journal, in a high-impact journal, Composites, actually showed and analyzed, list down all the research have done in the area of autogeneous and autonomous. So in all their technologies, as I earlier summarized. So, and this actually is one of the most recent paper already. It's 2020, published in one of the world-class high impact factor journal paper. And so we found that there's actually a research gap in this area, okay? Crystalline chemical admixture, and that's the topic that we are putting the gap here, okay, to contribute to the world knowledge, right? Yeah. So, and okay, so now before we talk about to tell us further about this, just to introduce about this area that we're talking about, crystalline chemical admixture. So what we are doing is actually I mean, we are putting some chemical admixtures in the concrete, okay, and this chemical admixture is not a new material actually. I mean, chemical admixtures have been added, okay, in concrete for decades, for example. And according to ASTM C125 report, chemical admixtures is just a material other than they are actually water, aggregate, cement. They are actually used to add to the concrete, mainly in the industry. It's actually for more of to increase its workability, plasticizing admixtures, okay, or maybe to reduce its controlling time to prevent cold joint formation, especially when you're talking about mass concrete casting in deep pile rough or thick transfer plate, to prevent the concrete from hardening first, so that to prevent cold joint formation, with a very practical reason. So to add on that, or to, so they are mainly, these are the main or to put air and training agent in parts of the Western countries to primarily to improve the resistance to freeze, thawing, and cycling reasons, okay, which are very practical aspects, okay, improve the workability, controlling the setting time, preventing cold joint formation in deep mass casting, and for solving a freezing and thawing issue. And of course, these admixtures are actually manufactured by a lot of big companies in the world, okay, like Lafarge, BASF, so and so forth. And besides producing this type of general type of chemical admixtures, they are also producing some of the very special newly developed admixtures, like corrosion inhibitors, shrinkage reduced admixtures, so and so forth. And our area of the crystalline admixture, in our area, crystalline chemical admixture, is actually into this category of miscellaneous admixture. Okay, so we are not talking about the general construction industry type of admixture, like as earlier mentioned. So typical chemical admixture is like water reducing, set retarding to accelerate for enable the structure to remove the formwork earlier. So you want to accelerate the concrete hardening. So these are all the typical type. A to G are typical type of chemical admixture, like for example defined in ASTM C494. Also the corresponding Euro code for air and training admixture, plasticizing, super plasticizing, accelerating, retarding admixture, water retaining. So these are all the standard admixture. And of course, like, as I mentioned, the main thing is that the main property with a very practical use is to increase the workability of concrete, to have a set control, either to make the concrete accelerate the setting time of concrete so that you can remove the formwork earlier, or some of the emergency repair issue, okay, because we need to concrete harden, or to slow down the setting time to prevent cold joint formation in mass casting. Now, one of the area we are actually going through in this is this aspects of durability. Okay, so now we are, of course, durability aspects on the admixture has been done. I mean, in the sense of water reducing, because the concept is that you're just using the water to cement ratio. They reduce the water so that the water to cement ratio will be lower. Hence, like then you can say that the concrete is more stronger. So they are just using this concept of increasing the concrete CSH to make it more durable. Or like for example corrosion inhibitors. So there is actually a very important area to further develop on this area of durability. That's why we are exploring in this area. Okay, because now why are we, as I mentioned again, why are we talking about durability? That, as I mentioned again, aging infrastructure. Okay, facing in the world, we are going to face like all buildings. Okay, like for example, all buildings actually in Eurocode 2, in the design of building, they actually specify a 50-year design working life. Okay, a 50-year service limit state design working life, where for 50 years by right, the Eurocode 2 for structural design means that in 50 years by right, when you build a building must be so-called habitable and people can use the building without any like water leaking, or the deformation is so much that people feel scared to live inside. So it must be serviceable in a 50-year period. Or for infrastructure like bridges, for example, it must be 100 years. That's actually stipulated in the Eurocode 2. Yeah. So that's why now and we know that a lot of structures after even about 30 to 40 years, it doesn't fulfill that limit. The service limit state criteria is not reached. But of course, as that mentioned, ultimate limit state of a structure is okay. I mean, the structures will be still standing, right? But what we mean is that in the for practical reason, we are not too concerned about the ultimate limit state, because it will be okay because it's reinforced concrete, so it will be still standing. But what I mean, the building has to be serviceable. You see, when we are building a building, we must let the people stay in the building, right? Yeah, rather than so that's why it must be. That's why we are concerned more about service limit state. Okay, and then with service limit state, durability will come into play. That's why we are going into this area. So now the use of crystalline admixtures actually since the beginning 2010, they actually have been used. Okay, they actually used in this area of crystalline chemical admixtures actually is to recover the performance and repair of cracks. Actually have been used since 2010, and in the recent ACI 20, the latest chemical admixtures published by ACI, the crystalline admixture are actually categorized as a permeability reducing admixture, or PRA. Okay, which actually used to prevent water migration in the structural concrete. Okay, so because crystalline admixture basically they are predominant. I mean, they are mixtures. Okay, some say they are hydrophobic, some say they are hydrophilic. So but predominantly they are hydrophilic, and they actually they react with water. Okay, and the cement particles. The chemistry, how it works is that they react with water and the cement particles in the concrete to produce the modified calcium silicate hydrate gel, and pore buckling participated in the micro cracks and capillaries. So that's the idea how it actually so-called solved under the permeability reducing admixtures. Okay, so it have actually been used since in the early 2000s, for example. So is this crystalline admixture is not new. What I'm saying is that we are actually exploring crystalline admixture in the usage of self-healing. Okay, so this application is new, but the usage for like permeability reducing is not new. Like for example, in the recent report from ACI 20, the latest 2016 report on chemical admixtures, there are many types of chemical admixtures, like I just showed you earlier. So in the chapter 15, it's called permeability reducing admixture, or this is what we call the crystalline admixtures. This is they're categorized under here. The report here tells us about the introduction, it can introduce you about the material, how to select and evaluate the material, how to apply it, and the dosage, and so on and so forth. So basically, as mentioned in the report itself, section 15.2, crystalline admixture, or you call the permeability reducing admixtures, as of 2016, they define. We want to know because this item, just to share, is actually a proprietary product and it's not a public domain information. So it's a lot of companies, they actually have their own patent. But now, but what we are sharing here is actually public domain information. So from there we learn from the basic characteristics, and then we do R&D to tweak its unique characteristics. Like what you know from the chapter section 15.2, to the crystalline materials, okay, admixtures, actually they consist of a proprietary active chemicals, okay, provided in a carrier of cement and sand. The hydrophilic nature of these chemicals causes them to increase the density of calcium silicate hydrate and generate pore blocking deposit that resists water penetration. So we are using some of these phenomena, okay, yeah. So but we are doing the literature review in these aspects of self-healing, okay, yeah. So when we are doing literature review, we review also, like just now, the paper from University of Cambridge, 2020 paper, and also some of these reports, yeah, to come up with a paper to review. And like and extract from the section itself from the ACI 2012, showing us reports, public domain information, that the crystalline nature actually can actually has reduce the permeability of concrete. Okay, the admixture, whether is crystalline, actually is very effective, 70% effective in reducing the concrete permeability of concrete, okay, compared to other types of a colloidal silical type of nature, for example. So they did tests. Okay, actually this is published in the figure 15.5 of that report itself. So it can shows you the comparison of the effectiveness of the coefficient of permeability. And we know that, indirectly speaking, when the coefficient of permeability reduced, concrete is more denser and the porosity will drop, and hence actually the pores actually will be lesser for the passage of chemicals and water to go through, and that indirectly actually so-called makes the concrete more durable and solve for the aging infrastructure issue. That's why we try to tap on these inherent characteristics. Yeah, but this actually is just a characteristics of permeability. But we are not talking about it's not yet talking about the self-healing aspects. So now, with that inherent capability, this permeability reduction admixtures, they are actually used normally for repelling rain in the current industry now. And for minimizing dampness. These admixtures can actually improve the quality of concrete pavers, tiles, bricks, blocks, okay, so on and so forth. And they can reduce the penetration of water into the concrete, thus delaying the effect of damage caused by freezing and thawing, and also the reducing the rate of moisture penetrating the concrete. Okay, so just to give us the background of the current usage characteristics of PRN. As I mentioned, actually the usage of crystal admixture actually been used and adopted in many parts of the world, and big multinational companies like Fosroc, Master Builder, Penatron, Zypac, Sika, they are all based in many parts of the world, and they actually have a team of researchers working on it to create some of to enhance its feature. Okay, yeah. Beyond what is currently reported, maybe like in the ACI 212, for example, 2016 report. So we are actually, and so us at AUS, we are also working diligently to try to use these aspects of crystalline admixture in the aspects of self-healing of concrete. So now, actually, so for the review paper, we actually did a review. Our team did a review of the crystalline admixtures, like from some of the suppliers and the public information domain from the journal papers and so on and so forth. And to summarize, what are mainly the characteristics of this, to let us be aware, what are the characteristics of these crystalline admixtures? They basically consist, okay, of they are actually irregular shape and they are powdered materials. So the specific gravity is a bit lower, it's about 2009, okay, compared to Portland cement, it's about 3150 kilogram per meter cube. Okay, so they're actually lighter than, you can say, Portland cement. So their crystal admixture, they are actually a bit lower density. Now, the key important is that when we break down the component of it, it actually has about 51% of calcium oxide and 14% of silicon dioxide. Okay, and this is actually a major component, as we know, if you learn in advanced concrete technology information, this is the building block of the CSH, the calcium silicate hydrate. This is basically the building block, the glue of the concrete. That's why we can use concrete now to build the tallest building in the world, like the Kingdom Tower, right? Okay, for example, now which actually, Kingdom Tower now is actually built in Dubai, for example. It's 1 kilometer high. Of course, it's now built 1/3, but because of economic reason, the construction is being stopped for a while. But Kingdom Tower is built in the one of the desert area under extreme concrete temperature, and it's 1 kilometer high, and it's a pure reinforced concrete structure. It's not even the steel structure composites. So there's actually a message showing that concrete is here to stay. So now, anyway, going back to the topic, so you can see that it actually has the building block of the cement itself. Okay, so basically, when I want to invent new things, I want to find things which actually have the same building blocks, right? Not, yeah. So that's the thing. And we also found that in some of the components, like which actually have potential on alkali silica reactions, which are not that good, also have some components there, like for example sodium oxide, okay, 6.41%, magnesium oxide. So okay, so I mean, so this and also these are some maybe significant in some cases of crystal admixture. So just let us be aware while we are developing things. Okay, so now the breakdown as shown in our review paper. The figure 1 shows the ternary plot of a crystalline admixtures, okay, in comparison with other cements. Okay, like for example, you can see that our crystalline admixtures actually is in blue colored dots here. It shows that it has a high amount of calcium oxide. Okay, this portion here, and actually is actually situated around the area of Portland cement. Okay, Portland cement. Okay, so GGBS is situated here. Okay, and then silica film, which has a high amount, about 99% of silicon dioxide, is situated here. Fly ash, okay, glass powder, okay, copper slag, and metachlorine, like for example clay. Those are also pozzolanic. So we actually want to know how are we located, basically. So the hydraulic region. So in conclusion, the hydraulic region, okay, it has crystalline admixture. Potentially, it has a hydraulic region of a similar chemical reactivity to Portland cement. That shows its potential for self-healing. Now, the main mineral composition, as of course we later found from papers and from this review, the review, okay, the crystal admixture actually consists of alite, baelite, ferrite, like ferrum oxide, calcite, Portlandite, calcium hydroxide in quartz, silica base. Okay, these are alite and baelite. Those are tricalcium and dicalcium silicate base. Okay, and a few gypsums they are found. So you can see that our review paper actually are focusing on crystalline admixtures. Okay, so so we are going zooming in on this area of where the one of the latest good paper, the top actually is here. So there's a potential gap there. We're zooming into this area just to let us show the significance of this presentation that we are doing here. It's quite a cutting edge, you can say that. Okay, so now the next thing is that after that we find the material characteristics. Now we talk about the compressive strength. So now we know, as a practicing structural engineer, designing buildings, consultants or builders, we know that compressive strength is a very practical and indirect indicator of a concrete microstructure state. I mean, just like a rule of thumb, a higher the concrete strength or lower the water cement ratio, we roughly know that the higher the concrete strength is more durable. It has lesser porosity, it has lesser permeability. The cement matrix is more densified. So that's why in structural design we always ask, the first question we ask, if anything in repair or diagnosis or what's the concrete strength? That's the first question we always ask, because we know, practitioners know that you ask the concrete strength, you get also the other material inherent things there, indirect speaking, for a first cut preliminary design examination first before we go and do the chemical analysis. So now that's why in some of the review paper that we found, people are actually studying the cracks in concrete to mass produce cracks. They actually introduce cracks because we want to study self-healing, so we want to introduce cracks into the concrete or mortar. Mortar here consists of cement, water, and sand without coarse aggregate. So sometimes, in some of the recent review papers, they actually introduce cracks by using this way, a very fast way to mass produce cracks. Okay, using by a control crack width method, where you control the rolling rate, and then you introduce a crack here. Then you put your product and see how fast it heals, for example. So this is a very fast way to do a material research, to observe the crack field under microscope, for example. So another way is actually people are also doing it. They load out all the way up. Okay, the recovery of cracking strength is also tested. Okay, by introducing the cracks by loading up to 90%. This is the current way. Actually, for my side, actually we are actually very interested in this area. We're working now. As of now, our research team, we are working on this area now. So now, from the review paper, we actually did a tabulation of the compressive strength chart on, like, for example, a compressive strength recovery of the cracks, for example. After you create a crack, right, how fast, how does the compressive strength recover? Okay, without crystalline admixtures and with crystalline admixtures. Okay, so, and we did a tabulation from the recent papers, international papers that we found. Of course, some of the specimens are subjected to the blue color, which are moist curing. Okay, so alternate moist and air curing. So predominantly speaking, from the chart itself, you can see that mainly for those with crystalline admixture, but if less than 7 days, okay, as of now, the current type of crystalline admixture we are analyzing is not so, it doesn't, the crack recovery is not that high, it's about 40%. Okay, but now when it prolongs, the longer the time you allow it, let's say for 28-day curing, okay, the crack recovery goes up from 40 to 80%. Okay, so comparing the result of mixers made with or without crystalline admixtures, okay, as of the literature review that we from our review on this crystalline admixture, there's no strong evidence yet that suggests that the use of crystalline admixture shows a clear advantage in compressive strength recovery. Okay, however, the effect of crystalline admixtures on the recovery is more pronounced when the mixers are subjected to at least a 28-day curing, for example. Okay, so, and moist curing and alternate moist air curing are found to be important to realize the recovery. So we found that it's very important to have actually the presence of curing, moist curing, for example, the situations of curing. Yeah. So I mean, so practically speaking, that's why. So when your structure is cracked, it's good to always put a gunny sack and spray water in. So it's important. So because nowadays we tend to like want to quickly demolish the formwork. So curing is a very important aspect. Yeah. So even in Singapore now, the Land Transport Authority, we are actually putting in codes to at least our structure cannot demolish the formwork fast. You must actually have a minimum period of time to enable on site to cure the structure first before you demolish the formwork, because curing, we know, is actually providing water for creation of CSH. Okay, yeah, from a chemical point of view. So now, when we are doing this study on this crack recovery, besides using the compressive strength method, okay, research papers have also found worldwide, they're actually using also 3-point bending tests are also used to investigate the recovery of the mechanical properties of self-healing concretes, okay, in the area of sometimes stress or load, okay, or sometimes and versus the crack mouth opening displacement, for example. So this is normally how they do. Typically, they have like a 100 by 100 type of concrete specimen, so-called. Then they either can be scaled. Then you put some rebar inside, of course, with a certain type of percentage rebar ratio, which actually you can actually simulate the real, like a real residential building. Yeah, in terms of percentage of rebar ratio. Now, then you load under a 3-point loading under this notch, okay, crack, okay, so that the crack can form from there, because we want to create cracks, you see. Then later on, we want to introduce some of the self-healing component, and then and see how it performs. Like for example, we load it up to the first loading rate. Okay, after it crack. Okay, then we actually reduce the load, unload the thing. Okay, then after that we want to maybe let the concrete, the gap here, seal, for example, either by putting into some like crystalline admixtures and so forth. Then we do the second loading to see how the performance after the healing. Okay, this actually, because it's relative. Okay, we want to find out how effective is our so-called this self-healing agent, for example, like crystalline admixtures is performing. So we sometimes in papers actually they have been computing the recovery ratio. That actually is the magnitude of preloading minus the unloading divided by the load of loading over the load of unloading. Okay, so sometimes people also measure in terms of stiffness. Okay, for example, in this aspect here, they're actually measuring the peak loads. Okay, yeah, this one method, they're actually plotting the stress over the crack mouth opening displacement. Okay, now, so the use of the crystalline admixtures actually will result in currently no significant recovery, okay, or improve recovery of the load stress versus CMOD relationship. Okay, as of now, the current paper that we found. Now, recovery is more effective, okay, when the specimens are exposed to moist condition, longer curing days, and also having a crack width less than 100 micrometer. This is about 0.1 mm. Okay, so and so, like for example, this is actually another view of the earlier picture. Is a more accurate view of the actual load CMOD diagram. So you load it to the first point, then you unload, then you load again. So this actually is a load CMOD curve. So and now we are actually in our research actually we tried to load up to when we load up to here the first crack. Okay, then in our research we actually tried to like for example, I showed you in this actually in some of our research we have done in NUS. Besides doing the load CMOD curve, we actually do also the load deflection. Okay, so for example, we load the first crack up to the when the crack goes up to about 0.1 mm, for example, and unload it. Then we let it seal. Okay, either by putting crystalline admixtures. Then we load the second time. Okay, yeah. So and sometimes we can load up to 0.3 because why we select some number here 0.3 because actually it's a service limit state crack limit. Okay, for example, and then we also like besides measuring the ratio on just now earlier mentioned, we also measure the stiffness. So it's relative. So now we found that actually the crack width when we do these micro cracks, right? Now we no need to load all the way up to 300 micrometer. We no need to load up to the service limit state. Okay, yeah, and we just need to because earlier part of research we wanted the concrete. Actually, ideally speaking, we wanted earlier part of research we wanted the concrete to able to self-heal by crystalline admixture itself when it can heal up to larger crack width, service limit state crack width of 0.3 mm or like for example it's 300 micrometer. That's actually stipulated in all the building codes all around the world, like Euro code, ACI code. Okay, so we wanted to do that, but we found that there'll be some challenge when you actually try to seal large cracks because like we mentioned also crystalline admixture, they are actually used to seal crack less than 100 micrometer. Okay, not 300 micrometer, not the service limit state. Later that doesn't actually affect on our thing because actually we found from the recent this very good Ryland paper, okay, that in the state of art report on micro cracking, they said that 10 micrometer, okay, which actually 0.01 actually is a visible hairline crack width, is taken as the upper limit, okay, of the micro crack width in the field of durability, okay, and lifetime calculation. So the limit of 10 micrometer is a structure which allow for fast interchange of fluid. So what it means that you see, I just want to share with us, like for example, this picture, like whenever when we do building inspection, for example, every like 5 years, for example, any institution in the world, right, will need to be mandatory by the inspection all the structure must go for building inspection, and normally they will report to the authority when your crack width have reached a certain type of service limit state. Either you reach 0.2 mm or 0.3 mm. So that is actually called service limit state according to all the structural code. I believe also India code also is the same, India Euro code, ACI code. So once it hit 0.2, 0.3, you need to be report to the authority, and authority will need to say, I will need to repair this thing, because these cracks are considered structural cracks. Okay, according to CNS definition, these are structural cracks. So it need to be the code will need to you need to repair this thing. So now so what we are saying here is that now we are not too worried about that, because when it hits up to 200 micrometer or 300 micrometer and above, the authority or the policy, or you can say human, will auto heal the concrete, so-called. They will repair the concrete by itself, by the policy. Okay, so in our area of research, we are talking about self-healing. So it's called the concrete itself automatically heal itself. So we are not too concerned too much when the crack width is bigger. Okay, yeah, as of earlier research. So if it's smaller, it's okay. So because you see, as long as it can heal, we want it to heal once it hit 10 micrometer. Means according to Rylam, that if it's smaller than 10 micrometer by right, the bulk of the water, because the water consists of molecules and surface tension, right? By right, may not enter into the concrete, that kind of thing, because of the bulk effect. So as long as our crack is actually less than that, it will be okay. Because normally when you do building inspection, a human can actually see a visible hairline crack width. Okay, you can actually see, but that doesn't mean that is a structural crack. Like shrinkage cracks, those are cracks. Okay, those are actually classified as non-structural cracks. So that's why those non-structural cracks, right? We wanted the concrete itself to self-heal, because the current policy now is that they won't repair this thing unless it hit about at least 200 micrometer. Okay, so that's why we are inventing a self-healing concrete which below the 200 micrometer it can self-heal. That's why we have actually done research earlier that found that we can actually effectively seal the thing up to even 150 micrometer. Okay, so that is good enough for our area of research, just to share. So so we initially last time we wanted to load up to 300 micrometer, and we found that it's not that easy. We even put fibers, but after that we thought more deep. We combine CNS concept and practical design and material side. We found that we no need to do up to 300 micrometer, because this one is human policy will repair the crack for you. You no need to have a self-healing concrete do so. So our self-healing concrete just need to do so to seal up to maybe 150 micrometer will do, and it's actually working. Okay, yeah. Okay, so now another method besides just now earlier mentioned about ways to measure the effectiveness of this self-healing, besides using compression cube and a 3-point bending test, is actually using a material method of using permeability and absorption of cracked concrete. This is actually one of the most common methods to evaluate the self-healing capabilities. So now, given that the crystalline admixtures are normally used as a permeability reducing admixtures, the assessment can be favorable for their inclusion in concrete. So we actually be subjected to that under permeability tests. We can actually compare, like for example, with those pure OPC concrete as a control mix, and those with the crystalline admixtures, then see how effective in terms of permeability and water absorption. Okay, yeah, just to share with us. So now in our also keynote paper, we also have this figure here. We actually tabulate recent research found by many researchers around the world. We actually extract the result and plotted a recovery of these permeability or absorption of crack mixes with and without crystalline admixtures. Okay, to see how is the effectiveness in terms of the recovery. Okay, yeah, we actually tabulated. So for water permeability, because as mentioned earlier just now, we are now going into this area, permeability and absorption. So now we found that if you have some of the paper we reported about 1.5 crystalline admixture content. So those crystalline admixture, where we are getting from? We're actually getting from those companies, like for example, those just now I showed, 1.5% content, 2.5% content, 3% content. What is the effectiveness in terms of the recovery okay, from absorption tests. Okay, so we actually so you can see there's a very high band here. Okay, very high percentage of recovery. That's very good. So once it crack means, like as shown, this recovery means what it means. Like for example, once it crack, then we put these crystalline admixtures inside the mix, then it's able to seal it, so it's able to recover. So then we measure its relative absorption. So we found, okay, that if you put so we tabulate the results, okay, either with pure crystalline admixtures, or some of the papers have some expensive agent, and we plot all the thing, and we found that, see, there's actually on a band of high recovery from permeation or absorption tests. Okay, and of course subjected to also, we also know the curing conditions. So the blue color line are those of moist curing, and those red color are air exposed curing, and yellow is a wet cycle. So that's why these mixers actually containing crystalline admixtures tend to show better recovery in terms of permeability and absorption rather than the reference mix. Okay, so in some cases, full recovery, for example, cracks are fully sealed, is reported as seen in water permeability tests. So the exposure conditions also we found have an effect on the recovery, where the moist concrete is shown to be conducive for self-healing, and air exposure work on work. Okay, and air exposure actually works the opposite lah. So you need to have water. So also the effect of we also found from the literature review that the effect of a wet and dry cycle exposure is inconclusive due to the limited study. Nevertheless, I think we still need to do more study because lack of data. Okay, yeah. So, and mixes containing combination of crystalline admixtures and expansion agent do not show greater recovery improvement as compared to crystalline admixtures containing crystalline admixtures. So actually, this is a summary of what we found. Okay, maybe first I take a 1 minute, 30-second break here, just in case to share whether am I reaching my audience, because now is a Zoom.
Yeah, sure.
So Dr. You all can see my slide, right, Dr. Gupta? Everything?
Yes, sir, sure.
Okay, good. Okay, then continue. Sometimes we have experience. These are the picture. Okay, good. Great. Then I'll continue. Dr. Gupta, may I know how much time I have now according to the time?
Maybe we are running 15 minutes late, so maybe in next 5 to 6 minutes if we can conclude the session.
Sure. Not this minute. Okay, sure. Yes, can. Okay, so now, actually the crack recovery, what we do is actually we use a microscope, okay, to see, and then this how we actually measure the crack width through the microscope. And so the crack recovery, as mentioned, we also tabulate from mixers using these mixers with and without crystalline admixtures. We tabulate in terms of their crack width, for example, and the average recovery of crack width we found using crystalline admixtures, okay, the data are quite high, okay. Yeah, especially when they are under the blue color with moist curing. So, as I mentioned, this part here, this part here works for us, is good enough already. We want to go, even though as long as you can seal up to 200 micrometer, we are okay, because we are letting the concrete to auto self-heal by itself by putting these crystalline admixtures. Because this part here, initially we wanted to let it heal, but then because the crack width is too large, okay, we found that it's not too easy. We even put fibers, for example, besides. So we found that it's not too easy. But then after that, we think through, maybe no need, because you see, this item here, once it hit 0.2 or 200 micrometer, for water retaining structure or pre-stressed concrete, the building authority, the government will always have a regular 5-year building inspection. They will monitor the building and they will stipulate that this is a structural crack. They will cause it to be repaired to the service limit state, because this service limit state has been reached. So now in our area of research, we are talking about non-structural crack area. So now using crystalline admixture, we actually found that it actually have a very good effect on working on 100 and 200 micrometer. Okay, that's good enough. That's good enough. Okay, yeah. So this promising research. Okay, yeah. So the overall crack result showed that the recovery of crack is affected by the inclusion of these crystalline admixtures. Okay, so and for mixers exposed to moist environment, the average recovery of crack mixer made without crystalline admixture, they are actually decreases as the crack width increases. Okay, yeah. So the overall result suggests that for a given crack width, the recovery of cracks is mainly highest in the moist environment when you add crystalline admixtures, followed by dry wet cycles, and air exposure does not seem to promote a significant recovery. So in our study also, we did some microstructure analysis of the crystalline admixtures to better understand on the mechanism to involve in the self-healing process when you use crystalline admixtures. So we did an energy dispersive spectrography analysis, okay, to suggest that actually calcium, oxygen, silicon, those are the building blocks of this CSH. They are actually present in mixes containing crystalline admixtures. So also we found that there's no sulfur peak, so there's no sign of the attringite. Now, the attringite actually is not too good because there's the one cracks in the concrete. It's quite expensive. So using this is quite we found that it's quite promising. Okay, yeah, because we did so microstructure study on the mixes with CSH. Some other microstructures studies actually we also reviewed from paper people have done also in the world, scanning electron microscope, which actually detect some of the needle-like products, okay, for those self-healing products in mixes containing crystalline admixtures. Okay, so and they found that CSH gels are created, calcium carbonate are deposited. So mainly calcium carbonate are mainly more of self-sealing product. They are not self-healing. Self-healing, as per definition, is that we want to create more CSH because this is the one heal in terms of structural strength, so-called compressive strength is being obtained. So there's actually healing. So in terms of, if you talk about calcium carbonate, you just put lime with water, you can actually seal the thing. It's just sealing. So this part doesn't build the CSH component, so it doesn't give the increased component. It just seals the thing, seals the crack. Okay, so there's two things: self-sealing and self-healing. So now we found that we did some microstructure studies. So we did also the X-ray diffraction analysis on mixers containing crystalline admixture that show that the main phase, okay, has a so-called promising components like, for example, we actually have a B for stands for Berlite. Okay, we actually open up the thing, okay, to open up the compound of crystalline admixtures. We try to see what is the component is. So it actually consists of calcium hydroxide, portlandite, consists of ferrite and barite, like calcium silicate, so on and so forth, silica. Okay, yeah. And so as I mentioned just now, the attringite. So just attach a picture here. Okay, so attringite, because attringite is in CNS. We are not too, it's not a so-called favorable element because if you look from scan electron micro, attringite are actually hexagonal crystals, in the form of needles, often found in voids and cracks in concrete. They cause cracks in concrete. Okay, yeah. So from that, actually, we found that there's no signs of attringite. Okay, so now just to recap for us, when we talk about pure cement chemistry, normally tricalcium silicate, dicalcium silicate normally in OPC cement. Right, we react with water, it forms the calcium silicate. This is the part causing the self-healing component. Okay, and then later on, as I mentioned, if also our cement normally have a gypsum and tricalcium aluminate. Okay, you react water, it forms the attringite. So attringite, this part actually is this is the one that caused the expansion of concrete. So this is the part, just to show you some of the basic from Sydney and minus some of the global textbook to let us be so-called catch up what I'm talking about in terms of this chemical. Why are we talking about this is the building block of the CSH when you talk about even OPC. Okay, this is the primary reaction happening. So that's why as shown, the microstructure overall result suggests that the healing mechanism of a crystalline admixture mainly involve further hydration of the formation of CSH gel. Okay, so it creates more CSH gel and also more carbonation for formation of calcium carbonate. So this is for self-healing. This part, calcium carbonate, is for self-sealing, just to seal the knee. Okay, so like for example, just to share, this is share some pictures of the scanning electron microscope of a calcium silicate hydrate. For example, this is a building block of a concrete. So usually the early product of the calcium silicate hydrate are actually found at the outer surface, and the late product. So because hydration are continuous, this is actually an unhydrated cement particle here, and this is water, for example. So normally, as CSH create, and just to share with us, when they talk about self-sealing or healing, these are the CSH. See, they actually build around the cement particles. Okay, so called the unhydrated cement particle, and then and of course then they traps the water. Okay, the water capillary field pores, and of course also creation of this portlandite. So usually when we want to talk about the one that causing this aging effect of concrete is actually this porosity. See? So we want to have a crystalline admixture. We actually can use the water here, seal up the water here, use up to create more CSH. Okay, so that's the basic idea. I mean, just to share from This actually very interesting, taken from Sydney, the global textbook. So now, okay, in summary now, the verdict on the future of crystalline admixture is that autonomous healing ability discovered in crystalline admixture, okay, is an added advantage in addition to the originally intended primitive reduction feature as stated in ACI 212. However, the results suggest that the autonomous healing ability of crystalline admixture is more prominent when concrete is in contact with moisture. Okay, so its application for water retaining and marine structure can be beneficial for both low permeability and self-healing ability. However, application for indoor structure with low humidity is unlikely as of now to provide any significant self-healing ability yet, unless we do more research on it. So now, comparing with other autonomous healing technologies, okay, developed in the recent years, like I shared with us just now the paper by Zhang et al. In 2020 in the journal paper Composites, right? They analyzed all the self-autonomous and autogeneous. That is a very good journal paper, okay, a very good review for all. So they studied, they found it. The other method like encapsulation, vascular system, and microbial environment. So the use of this crystalline admixture is actually relatively straightforward. Ours is not acquired encapsulation, and so because, like for example, like microbe, for example, even though you're able for our view, even though you're able to use some bacteria to cell, imagine, we always think from a very practical as practitioner or builders. Does the people want to stay in a building or work in an environment where you know that the concrete is made of bacteria? We ask ourselves this kind of question. People are talking about wellness, and when we're all working very hard, and people are spending most of the time in the family raising babies, like for example, small kids are growing up as a kid, and then working in the office for many years. You ask ourselves, imagine if our self-healing product concrete one have a microbe, will we feel comfortable? So these are some of the questions when we develop things in our side, we think of the practical. So that's why we're not working on our side, we are not working on microbes, for example. Okay, it's more of so that's why then crystalline admixtures can be easily specified in concrete design, and also production process of concrete made with crystalline admixture is actually similar to normal concrete. So that's why it's quite good. So at present, the research on the effect of autonomous healing ability derived from crystalline admixture now is still much an exploratory stage. Further studies on crystalline admixture may be emphasized on, especially on long-term effect, repeated crack healing cycle, like just now I showed you the two methods that we are doing now, upscaling it to real-life application in order to substantiate the reliability and its validity. So now, the research in our NUS lab, which we are actually investigating now, our research team is actually on autonomous healing ability and other hardened properties of concrete containing crystalline admixtures. And we're also developing chemical admixtures which actually can promote autonomous healing ability. Because you see, and then we're studying the long-term effect. You see, the motivation behind it is that the intention is that, imagine if our concrete can self-heal, then this structure can last longer, and then we don't have to so-called demolish the building. So, and it will be more so-called beneficial in terms of sustainable, right? Because some parts in the world, maybe which are for example, maybe very beneficial in parts of the world where the land is very big, for example. So some parts of the world, the land is very big, so the real estate price of a building it may be lower compared in small parts of the world like Hong Kong, for example, or Singapore. So sometimes the price of the place, let's say the price is expensive, then they might as well demolish the thing. But now in the major part of the world, like the land is very big, so sometimes the building cost itself is quite expensive. So it makes sense to make our concrete self-healing so that we don't have to demolish the building, right now. So we can save in terms of economic also. Okay, I'm just talking just to give us some view of where we're talking about places which are large land, right? So you'll be using this to prevent demolition is sometimes maybe more better. So conclusion, also the study reviews the current research knowledge on autonomous healing ability of crystalline admixtures, which are already intended to use for waterproofing as usual. And in general, the inclusion of crystalline admixture for autonomous healing tends to show favorable result. Further investigation to gain better understanding on characteristics of crystalline admixture and their chemical mechanisms in order to realize the full potential is also ongoing. So we actually show some microstructure studies. So we want to further develop to find out the cement chemistry of this. So main findings are now given here. So crystalline admixtures, we actually, just to recap, they actually have high calcium silicate product. These are the silicon product. These are actually the building blocks of CSH. Okay, so they actually have self-healing abilities, not just self-sealing. So they also have similar chemical reactivity like Portland cement, suggesting that crystalline admixture they actually require water for reactions. So the mechanical and durability, performance, recovery of the mixes containing crystalline admixture are found to be dependent on the exposure condition. Okay, which actually moist is more favorable. And similarly, crack sealing ability due to the use of crystalline admixture is actually more prominent when exposed to moist environment. Crystalline admixture are shown to be effective to seal cracks which are less than 300.3 or 300 micrometer, which is good enough for us. Okay, yeah, it's good enough. Even up to 150 or so, 200 micrometer is good enough. So the main self-healing mechanism involved in crystalline admixtures are further hydration of unhydrated cement particles. Just now I shown the SEM microcrop and the carbonation to form this calcium carbonate. So this part is the forming self-healing, carbonation. This part to form self-sealing. Okay, with that, Dr. Gupta, I think I've already ended my presentation. I hope it's within time.
Yeah, thank you so much, Dr. Kong and Dr. Lai, for presenting such a nice paper and such an in-depth study, so that we are getting knowledge how the world is moving with the self-healing concrete. You just don't have to rely on what we have built. You will build like that it will heal itself. So that's a great study you have done, and your work in your lab is really, I get to hear from your scholars that you are working in a pioneer field. Thank you very much again for gracing us and giving so much time for this whole ceremony to be here from Singapore, from your busy schedule. Just one or two queries which came up with some students and that you will be able to take. First query, although Dr. Lai has already replied, I will just again read to you. Can PRAs also function as water reducers?
Okay.
So Dr. Lai has
my research fellow, my team, Dr. Lai is actually one of our research fellow. Actually, he also worked with Professor Rajendra Deer from Birmingham University. In the world famous in recycled concrete. So actually also working with him on this recycled concrete. So besides our working on self-healing, we're actually working on recyclable materials. So actually, it's my passion. Also same as your Chancellor, Vice Chancellor. We hope to contribute also to a better world. Right, sustainable. That makes us work harder and more diligent to have a noble intention to benefit the world.
Yes, sir.
Okay. Good.
So one of the questions which also has came up is, can the healing work by providence of external moisture in dry areas also?
Mainly the more effectiveness actually is more, as shown in the paper, is mainly more for the moist condition. So for those so because they need water currently now, because this technology, so there may be potential in terms of wet cycle, dry and wet cycle, because there's more to reflect. We want to reflect also the natural environment, so that imagine a building is being built in crystal, then it can actually auto self-heal by that, because a normal environment, a building in a tropical region, we will have wet and dry cycle subjected to water. So we want it to auto heal when it's subjected to normal atmosphere. Now, practically speaking, when we talk about moist environment, in order to do that, then if we really want to repair this thing on let's say our concrete is being used using crystalline admixture mixed design. So when we found that so-called this kind of hairline crack, which are non-structural crack, mainly contractor maybe just put a garnish sack and then spray water. That also is a practical solution. Right, it's not so costly.
Have you implemented also, sir, this crystalline admixtures anywhere in Singapore with some as you are working with the industry also very closely?
Yes, actually, the Housing Development Board of Singapore is actually looking into this also. Actually, this research is also is a government funded project.
Okay. One thing from my side also. Here in Himachal Pradesh in India, we are having many historic structures which requires rehabilitation and retrofitting. Can crystalline admixtures coating kind of or a kind of a wrap be adjusted to that, so that the self-healing property is induced into the structure? Is there some research going in this direction also to use crystalline admixtures in retrofitting purposes?
Okay, that's a good question. And also, so now I'm talking about this so-called historical structure. So may I just ask us, like in Himachal Pradesh, those historical structures, are they what is their base material? Are they like mainly mortar or means a cementitious base? Or are they?
No, they are mainly based on the local stone available and the mortar, which was based on mud and lime.
Okay, mud lime means they got kaolin. It means they got this metakaolin, all this. So they have the calcium oxide and silicon dioxide component.
Yes.
Yeah. Then it's good. I mean then it can help lah. Of course, the component there, it may not be so, because the base material itself is not that solid as a OPC Chem 1 cement, for example. Because the amount of calcium oxide, it may be lower, for example. So so when you are using these crystalline admixtures, in terms of structural, you talk about repair first lah. Talk about repair first beside yeah, we can it can help lah, in the sense because this one crystalline admixtures, when you mean to apply like a coating, is it? Like you apply like a coating, for example, like cementitious base, because the base material is not that strong, yeah, for repair. So once the base material is not that strong for repair. So now when it cracks, right? So you use these crystalline admixtures, okay, to cast a concrete new type of concrete mix, repair mix. Then you patch the gap, you patch those cracks, yeah. Then it will help. You need to make sure of the concrete compatibility, means because the concrete strength is a bit low, for example, then maybe grade 20, for example, you don't use because this crystalline admixture you can actually mix to a high strength also. So you don't mix a high strength to low strength. Mainly if it's the base material is like low strength 20, for compatibility it's best to do like similar or 20 to 30. You don't use a grade 70 crystalline admixture then to put on that. Yeah, then because they will create an incompatibility issue, it will cause the force transfer. End up crack will happen other place of the structure. That's the thing, because normally the force in the structure, they flow to where it's more stiffer. The more stiffer is it, the more attract the force. So now yes, it will just you will use the thing for because the crystalline admixture, as you know, the base material also have its own calcium oxide and silicon dioxide. It contributes this thing, so it will use to seal up its own gap there. Yeah, so it can help. Yeah.
So in theory, it should work.
For repair, yeah. But I mean, for talking about retrofitting, okay, because I'm thinking about repair. Talking about retrofitting, by right, it's better to use like fiber reinforced plastic, FRP, to strengthen.
Yeah, but for historical structures, it becomes a sentiment issue for.
Okay.
So you cannot have solutions with them. So that's why we are looking for a solution which remains, the beauty remains, and we can have.
May I ask a question? Because FRP wrap, you can actually wrap it. I mean, in Singapore, we actually wrap it, and then you actually put a plaster. Then, like in Singapore, like some are doing, we wrap it. Then we put the plaster. End up, you don't see the thing,
Yeah, then there are some additions to it but it will give a layer and a thickness to it.
Okay.
So that can have an impact on the historical significance of the structure.
Okay.
But you are anyways working very closely with these crystalline admixtures, so we will also like to have a go with them here at our lab, and let's see how these works out for us also.
Okay. Yeah, good question.
Again, thank you so much, sir, we have taken your lunch time also fully.
Yeah.
So staying there from Singapore and helping us all out. And we hope that in future we can have more of collaborations with JUIT and with students from our institute and NUS under you or under other professors also.
Yes. Yeah. Also, I also happy to able to work with you all. Yeah. And also, one of my former research fellow, Dr. Pankaj Munja, he's also a very good, very, very diligent researcher, and you also from JUIT also. So producing brilliant scholars from here, from your country, right? Yeah, very good. So we will continue to work hard to benefit the world. Good. Yeah.
Yes, sir.
Yeah. So I think now is the session now is to go to another speaker, right?
Yes.
Okay.
Now, another eminent speaker we have
Okay.
waiting for.
Great.
Thank
Okay.
you, Dr. Kong. Thank you, Dr. Lai also.
Okay.
Sir.
Take care all.
Okay.
Okay. Bye-bye.
Bye-bye, sir.
Bye-bye. Yeah.
Bye-bye, sir. With this, now the first keynote speaker, Dr. Kong, has spoken, and now we'll move ahead to our second keynote speech for the day, and which will be delivered by Dr. Souradeep Gupta, and he is with us. I'll just introduce him once, and with the introduction, I'll request Dr. Souradeep Gupta to further go ahead. Let me just present a brief introduction about Dr. Souradeep, and then we can wait. So a very good afternoon now, Dr. Souradeep. He is working currently in Center for Sustainable Technologies at IISC Bangalore. He's assistant professor over there, and he is leading Material Engineering Research Innovation and Application Lab, which is the material group, which focuses on additive manufacturing and development of low carbon buildings materials. He obtained his PhD also from National University of Singapore, followed by a postdoctoral research at the University of New South Wales, Sydney, Australia. He is recipient of Discovery Early Career Award by the Australian Research Council. Dr. Gupta has founded and currently leading a bio-based material technology company based in Singapore aimed at commercializing biochar-based building products. He has conducted extensive research in the areas of self-healing, bio-based building material, and carbon sequestration. Dr. Gupta has published 28 peer-reviewed journal articles, more than 10 technical articles in conference proceedings, 3 book chapters, and a patent also. So he'll be our second keynote speaker for the day, and he'll be deliberating on investigations of biochar from biomass waste as a carbon sequestering admixture in cement-based building material. Dr. Souradeep, a very warm welcome, and I would like to hear from you.
Yeah, thank you, Dr. Tanmay, and I extend my sincere thanks to the conference organizing committee. I see a large attendance, and I believe all the passionate people are here to learn more about sustainable structures, buildings, and materials. So with that, I'll share my screen.
Yes.
So I go ahead. Can you all see my screen now? Tanmay, is it visible? Okay. Yes. Okay, fantastic. So yeah, as the name suggests, I'll be talking on application of biochar from biomass waste as an admixture for cement-based building and construction products. I'll also take cue from Dr. Kong's lecture. He has set the stage for self-filling concrete, which I'm also going to talk a little bit towards the end of my talk. So just a brief introduction. I'm Dr. Souradeep, and I'm currently an assistant prof, and I've also recently received this early career award from ARC. 2 years ago, I also co-founded a company called Biochar Innovations Private Limited. It is based in Singapore, also funded by partly by NUS and partly by Singapore government agency to commercialize and develop biochar-based building products for both structural and non-structural applications. So here is a brief overview of my talk. I'll be talking a bit about the center I'm working at currently and my research group, what it does, what are the research focus. I'll be talking about the importance and suitability of biochar as a construction material. I'll extend my talk with some application examples, what are the properties we should look out for, and certain special applications of biochar as a self-filling supplement. I'll conclude my talk with some future directions in the area of sustainable and low carbon materials. So I work at a beautiful center called Center for Sustainable Technologies, situated among the lush greenery of IISC Bangalore. We are an interdisciplinary center. We look at several sustainability issues that are of global concerns. For example, renewable energy, hydropower and other sources, waste to energy projects. We work a lot on water purification, defluoridation, treatment of black and gray water. We have done a lot of work for the past 25 to 30 years on sustainable buildings, on sustainable building materials and building integrated photovoltaics. And we have made really some good translational research and contribution to the industry and the whole landscape of India as far as buildings are concerned. We also do work on the environmental issues such as solid waste utilization and climate change. The group that I'm leading currently belongs to the building cluster under CST. And broadly speaking, we work on two different technologies. You can always integrate this, but I will like to categorize it for now under low carbon materials and additive manufacturing. So the low carbon materials, we take a few different mechanisms to achieve that. One of that is carbon sequestration, how we can reduce the net carbon footprint of cement-based construction products, and how we can also develop or rather upcycle wastes generated locally and use it as a cementitious admixture and binders. On the additive manufacturing front, I just started this new program at CST. We are focusing both on polymer printing and concrete 3D printing, and we are looking at special applications, for example, environmental remediation, also promoting biodiversity, and doing some kind of research in the area of affordable buildings and housings. So with that, just let me give you a brief idea about what motivated me to start this research, which I did about 7 years ago as a graduate student at NUS and concurrently as a postdoc and now as assistant professor at CST. When we started this research, one of the big problems that actually struck us was that of waste management and particularly the bio-waste management. You know, Singapore is a small country, about 720, 730 square kilometer of the mainland area, but it does produce a lot of biomass waste in the form of wood and horticultural waste because of the high or large green area in the small city state. So what is usually done is that this kind of waste is incinerated with other kind of waste such as plastic or metal wastes, and those are really contaminated. Those are in ash form, and they're transported eventually to another island called Pulau Semakau. Pulau stands for island, which is 7 to 8 kilometers off the mainland, right? So this whole process is associated with a lot of emissions due to transport and due to the incineration methodology. Not too long ago, this incident also happened in Singapore. Okay, just let me turn on my pointer. Happened in Singapore that a pile of wood waste near the northern part of Singapore actually caught fire and it emitted a lot of volatiles and organic gases, and that caused a lot of disruption in the region. This photo, most of you will be familiar with this. This is a farmer practicing open burning of the crops, the stubbles that are left over after the harvesting season is over. And as you know, this is the fastest and rather the easiest way of get rid and preparing the land for the next harvesting season. And we all know, and particularly as you are situated in the northern part of India, you will be facing the problem of pollution due to particulate matter emission, and the same thing happens in Delhi and other nearby areas, and also the pollution due to the emission of carbon dioxide and other toxic gases. Towards the end of 2019, Australia did face a similar kind of situation, and many experts, of course, attribute this to the rapid climate change happening in the region, that an extensive bushfire happened throughout the country, and that was just before I landed in Australia, and I couldn't go there for about 3 weeks because some airports were shut due to the bushfires and the emissions caused by them. So you can see that huge amount of green land and open land are being destroyed due to this climate change. And we really should find a way to actually harness the biomass waste that are generated in the country and use it as a value-added products. We are not the first team to actually trying to advocate this. Many researchers have in the past tried to use biofibers, for example, natural fibers as reinforcement in cementitious products, or even as particle admixtures in cementitious building product. But the main issue, apart from the low tensile strength that is faced in such kind of application, is that of the degradation of the lignin, hemicellulose, and cellulose in the cementitious admixture due to the high alkalinity of the matrix. So what happens is that hemicellulose and cellulose are being stripped off from the surface of the fibers and particles, and those are sources of sugars that cause a lot of problems such as retardation of cement hydration, or it even threats durability of the buildings, or rather the material in long term. This is a scanning electron microscope photo. I borrowed it from Way and Meyer, published in 2015, and it shows a vegetable fiber being disintegrated in the cementitious matrix. So in summary, if you have a lot of hemicellulose and cellulose, these are the two major components in the natural fibers and particles, it may cause a lot of such issues. So what we did is we thought of a strategy. It's a thermomechanical treatment called pyrolysis, which can be used to actually convert the biomass waste, which can be a wide range of waste such as agricultural waste, food waste, or even wood wastes, under a controlled set of preparation conditions into a solid product called biochar, and the other co-products of this process are bio-oil and biogas. In India, as we all know, that biogas has been long used traditionally, especially in the rural parts and peri-urban areas, as a source of fuel. Bio-oil can also be used to offset some fossil fuel usage, and it can also be used as a pesticide, as some farmlands and farmers in Australia have demonstrated that it can get rid of some harmful insects and other pests from the farmlands. So if we take into account the utilization of all these products, the whole process can actually be carbon negative. I'm often asked this question that, well, what is the difference between biochar and charcoal that you usually use for barbecue and other applications? The main difference is that biochar must be produced under a controlled set of conditions, right? If the conditions are not controlled, for example, the temperature and heating rate, the properties of biochar will be very different, and in some cases cannot be used as an admixture in cementitious composites. If you look at biochar under a scanning electron microscope, you will see this kind of macropores on the surface, which are actually originated from the original structure of the plant biomass. These channels are basically the transport channels for food and water, and even the nutrients into the plant body. These macropores do serve a lot of unique functions. However, I will later discuss that this is not always favorable, and biochar needs to be processed before even application in cement. There are certain environmental benefits of biochar. One is that the meso and the micropores of biochar can actually absorb carbon dioxide due to the high surface area and other toxic gases, as well as the gases of sulfur and nitrogen. And that can actually be extended to water filtration and air filtration applications. Biochar has been a subject of research for over 30 to 40 years now, and most of the applications have been focused towards agriculture and soil enhancement. Based on that, many researchers, based on life cycle analysis, have shown that usage of biochar in large volume can reduce global anthropogenic emission by 12%. And how does it do that? It's because of the carbon that is sequestered in the structure of biochar instead of being emitted to the environment, and that can contribute to 870 kg CO2 equivalent per ton of dry feedstock. However, a word of caution here: when we are talking about such numbers, we must be careful about the feedstock and the preparation condition of biochar, because the carbon content in feedstock will vary from precursor to precursor, and therefore the carbon sequestration potential will also vary consequently. So of course, it's also a means of waste reduction and recycling, because the biochar can be used as a filter, as a soil enhancer, or even, as our research shows, as a cementitious admixture to improve the properties. We are not the first group who ventured into this application of biochar as construction and building materials. It was first demonstrated by Choi et al. In 2012, showing that 5% biochar by weight of cement can actually improve compressive strength of mortar by 10 to 12% if produced and processed properly. Schmidt in 2014 then actually initiated a few demonstration projects, and one of them being the Ithaca Institute in Switzerland, and they used biochar-based wall plaster to coat the internal walls, and they have found that it acts as an excellent regulator of moisture and humidity in the indoor environment. It doesn't always have to be black, although I borrowed this photo from one of his websites. There is also a wall plaster which is white in color. Some pigments can be mixed and dessert color can be obtained. Ahmed et al. In 2015, they are a group from Politecnico di Torino in Italy. They also reported similar findings that biochar can be used to improve toughness and compressive strength of cement paste, then control, which is maybe up to 40 to 100%. However, when we are talking about building and construction applications of biochar, we are not just focusing on the mechanical properties. We should look at it holistically. For example, what is the effect of an admixture, of a new admixture, on the fresh stage properties such as rheology, hydration, or even on other durability properties such as water permeability and shrinkage. So we started this research in order to highlight how biochar can actually affect the fresh stage property and the durability of constructions. In today's talk, I'll be focusing on these first three areas. We have ventured into other areas, for example, even evaluating the application of biochar under aggressive environments, for example, elevated temperature and high amount of dissolved chloride and sulfate in ground and seawater. So those papers are already published and you can always refer to that. However, in today's talk, I'll be focusing on the general application or the general findings pertaining to application of biochar as admixture in cement. I'll be talking on carbon sequestering potential of biochar cement composites, and this can be a potential means to develop low carbon materials, and that is very important in the context of today's climate change and sustainability. Towards the end of my talk, I'll be focusing on special application, biochar enhanced self-filling in fiber reinforced concrete, and we have evaluated that under single and a few more loading cycles, right? Just 2 years ago, as I shared before, that we actually founded a company called Biochar Innovations Private Limited with the generous support from National University of Singapore through their Graduate Research and Innovation Program, and also a Singapore government agency called Enterprise Singapore. They extended their support to help us upskill the production and commercialization of biochar in non-structural building products for different kind of applications such as wall panels, facade panels, and other pavement applications. So that effort is ongoing, and we are putting a lot of effort into evaluating different kind of feedstocks and preparation condition to have a more sustainable approach towards biochar-based concrete products. So you can check out our website here, which is mentioned, Biochar Innovations Private Limited. However, what makes biochar a suitable candidate for application in cement, right? So we need to look at a few fundamental properties of biochar. So if you look at the scanning electron microscope, you can see a lot of macropores. These macropores, depending on the dosage of biochar, can actually affect strength development positively or negatively, because these macropores can actually absorb water in the initial stages and can retain it and later serve as internal curing agent in cementitious composite. However, they're not always beneficial when we are talking about certain applications under aggressive environments. However, biochar can actually be processed very easily. It can be grounded into very fine particles. As you can see in this, about 2 to 3 micron particles are present. Even some particles are in the nano range based on the particle size distribution analysis. Although you cannot see a lot of such macropores on the surface, these particles do contain a lot of meso and micropores. And those are also very important in the context of cementitious composites. And how do you find that out? You can do a gas absorption analysis using nitrogen or helium, and you can find out the pore volume based on that gas absorption. And based on this plot, which plots the pore volume versus the pore size of such fine particles, you see a lot of pores being actually concentrated in the nanometer range, about 60 to 70 nanometer. So these pores are fantastic in absorbing carbon dioxide. They can absorb up to 2 to 3 millimole per gram of CO2 in the pore structure and can act as a filtering agent and also a carbon sequestering agent. There are other properties such as specific surface area that are commonly investigated for any kind of admixture, if you are talking about fly ash, silica fume, or even slag. And biochar, it has a high pore surface area as well, of course, due to the meso and the micropores being present. And also the porosity of biochar is very important before we consider its use in cement. Why is it so? Well, you do not want an admixture with very high porosity. You may want that depending on application, but not in all cases. So you must be mindful about the kind of porosity range you are talking about. It can vary over a wide range. It can go from about 18 or even slightly lower to up to 30 or 40%, right? So there are other compositional aspects of biochar, for example, the CHNS content, carbon, hydrogen, nitrogen, and sulfur. Based on our evaluation of wood-based biochar, the sulfur content is very, very low. It's less than 0.1%, so I haven't put it here. However, the carbon content, depending on preparation, varies between 70 to 90%, right? And there is a very important parameter called oxygen to carbon ratio. And why is it important? It is because these actually represent, or rather qualitatively represent, the stability of biochar in cementitious composites. So let's discuss a bit more on that, on the stability part. So we have done a lot of X-ray diffraction studies of biochar prepared at different temperature from different feedstock. So here is an example of the raw biomass, which is sawdust in this case, and biochar prepared at 300 degrees and 500 degrees respectively. So in this case, you can see a bit of a broad hump here for the raw biomass, and also a broader peak around 22 degrees, which correspond to hemicellulose and cellulose, which are partly crystalline and partly amorphous. So if you're preparing biochar at 500 degrees, you will see that both this hump and this broader peak has actually disappeared, and this is more of an amorphous signature from XRD, and that suggests that both hemicellulose and cellulose, which are otherwise the harmful components in the biomass, have been decomposed. And this kind of biochar is more suitable to be used in cement and concrete, because in that case, they would not affect the hydration properties. Spokus in 2010, he actually compiled about 1,000 of data points to find out what is the predicted half-life of biochar in relation to the oxygen to carbon molar ratio. So here are some of his data that he compiled, and you can see that based on the preparation temperature, when you increase it, the predicted half-life of biochar increases due to the consequent reduction into oxygen to carbon molar ratio. Right? And why does it happen? Because when you increase the preparation temperature, more oxygen containing groups are actually removed, and more carbon as a percentage of the total mass is being formed. And therefore, it reduces the oxygen to carbon molar ratio drastically. However, I should mention that this predicted half-life was done under a natural environment, or even in some cases soil environment, which is slightly acidic or neutral in nature. So in case of cementitious composite, which is highly alkaline, we must do a separate investigation on that. However, if biochar can show high stability under acidic environment, it is actually good. It's a very positive trend. Why? Because biochar is alkaline in nature. The pH is about 8 to 9. So it may not react very detrimentally in alkaline matrix. It can stand the test of time in case of acidic environment. So let's take a look of how biochar actually influences the fresh and hardened properties of cement composites, right? So when we are talking about cementitious composites, for example, mortar and concrete, rheology and flowability are very important parameters to demonstrate the workability of concrete, whether it can be cast with relative ease, with traditional techniques, how it can flow, right? So we did a lot of investigation using static test and dynamic shear stress of biochar-based cement paste, and the main objective of such tests using this kind of rheometer, which relies on a concentric type of cylinder and a shear vane, or you can call it the rotor, that applies a torque and measures the resistance, and based on that, it finds out what is the yield stress, that is the minimum stress needed to initiate flowability, and the viscosity of the mixture, right? So we did this investigation at different time points, from 3 minutes after mixing to about 30 minutes from the time of mixing. And very recently, I also conducted a series of tests with up to 75 minutes from the time of mixing using biochar cement paste. However, it is not, the results are not here, and it is under review currently. So you can see a general trend that when you increase the dosage of biochar from 1% by mass of cement to 5%, there is a trend of increase in yield stress. And same trend also exists in case of plastic viscosity. There are two reasons why this kind of trends are observed. One is that the fine particle size of biochar, which increases the packing, and it reduces the fluidity of the mixture. The second reason is the water absorption and retention by the meso and micropores of biochar in case of the fine particles, and that actually absorbs a part of water and makes the mix more viscous. So if you plot the flow spread against the plastic viscosity, you will see that they're correlated very well, because if the mixture is very viscous, the flow tends to reduce. However, in this case, no superplasticizer or even water reducers were used. So if you use that, you can actually maintain a desired level of flowability in case of biochar concrete and biochar cement. So a certain dosage of SP will be needed in that case. How does it affect the hydration kinetics? And that is very important when you are talking about removal of formwork and also developing early age strength of cementitious composites. So what we did is we compared the hydration kinetics of 1% and 3% biochar by weight of cement in cement paste, and compared that to that of a control, which is the plain cement paste. So if you see the heat evolution curve, which actually represent how fast the hydration reaction is taking place, it shows an increase in the rate of heat evolution about 8 to 9 hours from the time of mixing. And if you plot the cumulative heat, you also see a slight increase after 48 hours from the time of mixing due to biochar addition. If you mix biochar with fly ash, it's a hybrid combination. We're testing a lot of hybrid admixtures with fly ash, GGBS, that is slag, and also silica fume to have a more percentage of cement replacement. You see a similar trend that adding biochar increases the rate of heat evolution, or rather the rate of hydration of cement. And how does it happen? It is explained through the schematics here. So if you take the case of plain cement paste, these blue circles are actually cement particles suspended in water, right? So all the voids and the capillary pores will be filled with moisture, and the hydration will take place around the cement grains, which are represented in these grayish circles. If you add biochar, which are way finer, about 8 to 10 times finer than that of the cement grains, these particles fill up the spaces between the cement grains and also the voids and the capillary pores, right? So the biochar particles, biochar is itself inert. However, the particles which are in close vicinity of the cement particles actually act as centers, or rather nucleation centers, for the precipitation of hydration products. So all in all, we are increasing the surface area for hydration reaction. And as we all know, based on our basic chemistry, that when you have a high surface area, the reaction takes place in a more accelerated manner, right? And that is also visible based on the scanning electron microscope photos that you can see. It is taken about 15 to 16 hours from the time of mixing, and you can already see some precipitation of hydration products taking place on the biochar surface. This also happens in case of the macropores of biochar, right? Because the macropores actually absorb a part of moisture, and that provides a conducive environment for the hydration to take place within the pore walls of biochar. So in this, or through these mechanisms, the hydration kinetics is accelerated in biochar cement. This is also reflected in a longer term degree of hydration based on XRD and also the thermogravimetry analysis. So XRD is actually a qualitative way that you can show that how hydration is influenced due to addition of admixture. It can also be done quantitatively. In this case, it is a qualitative analysis based on the height of peaks, or rather the intensity of the peaks corresponding to calcium hydroxide, which is CH in this case. So if you compare the plain cement paste and that of the biochar paste, you can see a very substantial increase in the peak of CH. The same happens in case of the combination of biochar and fly ash, and that demonstrates that more hydration products are being formed. It is rather difficult to quantify CSH based on this, because CSH is not totally crystalline in nature, and it doesn't show in the form of very noticeable peaks in case of the XRD spectra. So we have to rely on the formation of calcium hydroxide. The same trend in a rather quantitative manner you can see in case of the degree of hydration through thermogravimetry analysis. So the degree of hydration can actually be calculated through different formulas. For example, Bhatti's method, which takes into account the chemically bound water in cement hydration products. For example, CH, CSH, or even some calcium carbonate, right? So if we add some biochar, we can see that the degree of hydration is improved by about 10 to 12%, depending on the dosage of biochar, and the same goes for even the fly ash mixes, right? And that is again attributed to the fine particle size of biochar and the acceleration effect on hydration. More importantly, we want to know how does it affect the bulk properties, right? For example, the compressive strength and other durability properties, because that is the quality assurance techniques or methods we use for practical applications. So if you use a biochar, and here the early strength developments are shown, that adding biochar improves the compressive strength development by 22% compared to that of control, right? And the percentage improvement actually depends on the age of the mortar or concrete, right? So at early stage, biochar has a noticeable beneficial effect on strength development. And the same can be seen in case of fly ash mixes. This is rather encouraging to me. Why? Because when you add fly ash, the strength development, at least in the early stage, is retarded. So many industries, prefabrication and precast industries, they use a lot of chemical admixtures or even other thermal treatment method to accelerate the rate of hydration and strength development. So having biochar in the mix can actually improve the strength development, and some of these measures can actually be mitigated, which are energy intensive. So if we actually plot the compressive strength of the biochar mortar to that of the cumulative hydration heat of a representative cement paste, we can see a very good correlation between these two, right? And at early stage, that usually happens, and that has also been confirmed in other studies, that when the hydration heat is higher, the kinetics is higher, the early strength development will also increase. And this is of particular interest when you are talking about formwork removal and construction productivity. So probably if we have to wait for 7 to 8 days for the removal of formwork in plain concrete, we can reduce it to about 3 or 4 days in case of biochar concrete, because it reaches that similar strength level at early age. How does it affect the water absorption, which is actually a measure of permeability? And this is a very commonly used technique to find out how much permeable channel for the intrusion of external fluids happen in concrete. So based on that, based on the amount of water absorbed, which is shown in the y-axis in gram per centimeter square cross-section area, we see that adding biochar actually reduces the absorption of water through capillary action. As I shared before, we are also testing a lot of hybrid admixtures like biochar and silica fume, as you can see in this case, and that also shows significant reduction in absorption compared to control, but well, not compared to silica fume mixes, because silica fume, as you also know, is very fine, and it also has high pozzolenicity, right? So the results are quite encouraging in that aspect. Another test that we commonly do is that of water penetration according to British standard BACN 12390. That is the code that we follow. However, we do some modification for a conservative estimate of water penetration. We increase the pressure of penetration, pressure of the water that we apply, and we find out the depth of penetration of the water. And that is actually a very important test when you are talking about the integrity of the cover concrete in case of reinforced structure, because we do not want the contaminated solutions to penetrate and trigger reinforcement of steel. So this is how we can evaluate the integrity, and this shows that having biochar can reduce the penetration by about 40%, and this can be further reduced if we use together with other beneficial admixtures such as silica fume. And these are all attributed to the fine particle size, the filler effect that biochar has in case of cementitious composite. It plugs the pores, it reduces the capillary porosity, and thus reduces, or rather improves, the water tightness and reduce seepage in concrete structures. There is another very commonly happening durability issue in concrete structures, the shrinkage cracking, which takes place from a few hours of casting to up to many days, depending on the type of shrinkage happening. So this early shrinkage is not actually a threat to the structural integrity, but it is always a threat to the durability in long term, because such micro cracks being formed due to shrinkage can contribute to water penetration and can trigger other durability problems. So we wanted to test different combinations. In particular, two combinations are shown here. One is that of biochar added at 3% and a combination of biochar and silica fume. And you compare these two mixes to plain mortar and silica fume 10% to see how it affects depending on the base composition. So if you see at the sill shrinkage, which is the autogenous shrinkage due to self-desiccation, having biochar can actually reduce it at a very early stage and even at a very late stage by about 48%. And why does it happen? This is quite apparent because of the internal curing effect, the desorption of moisture from the pores of biochar at a early and later age during hydration. So if you compare with that of silica fume mixes, the reduction is even more prominent because silica fume increases the rate of self-desiccation, and having this kind of porous admixture can improve or reduce the shrinkage. If we are talking about drying shrinkage, then the trend is slightly different. If we compare to that of plain mortar, control in this case, which is shown this blue triangle, we don't see a very significant reduction due to addition of biochar. There is a slight reduction, but it's quite comparable. However, if you compare with that of silica fume mixes with 10% silica fume, there is a very high reduction in the mixes containing hybrid of biochar and silica fume. So in summary, biochar can actually be a good agent for internal curing under sill condition. However, when you expose it to the external environment right from the start, about 1 day age after casting, it may not retain as much water as in the case of sill condition. However, in case of silica fume mixes, it can definitely contribute to the likelihood of shrinkage cracking. And this is also encouraging because silica fume is also being used widely for high strength concrete and high performance concrete. And this can be a potential solution of mitigating these durability issues associated. I'm often asked, what is the long-term implication of having biochar in cement? Will it reduce the strength? Will it affect the durability? And thus, about 3 years ago, we studied we initiated this study together with Korea University with 10 different types of biochar produced from different feedstock under different preparation conditions. And we kept all these mortar cubes in the lab under dry conditions, right from the 28-day age up to 2 years of age. And some of these are still kept in the lab because we hope to test after 5 or 6 years and how does it affect the durability and compressive strength. So based on this 2-year perspective, we can see that having certain kinds of biochar actually continue to improve strength compared to the plain mortar, which is the control mixtures. The trend is definitely not the same in all cases of feedstock. For example, cotton stock, if you see, it's quite comparable because the fundamental composition of the biochar being produced are different, right? So it also depends on the biochar that is being used. However, the encouraging fact is that it does not pose a threat to a slightly longer term, in this case, 2-year window of strength development of cementitious composites. So more studies would be needed to extend this to maybe 5 years, 6 years, or even considering the service life of building. We have to simulate that to 30 or 35 years to see how it affects. So based on even the microstructural investigations that we did, there is no other products being formed. Biochar is mostly inert in cementitious composite, and it just acts as a filler in this case. So taking a step ahead, last year I initiated this study on the carbon sequestering potential of biochar mortar during my time in Australia as a discovery fellow. And we actually wanted to study how it can contribute to the reduction of carbon dioxide emission associated with cementitious products, right? What motivated us? Because if you see the current context, the ongoing COP26 taking place, even before that happened, a subcommittee actually came together and set some full building decarbonization targets and concrete policies to tackle the issues of rising carbon emission from building and construction sectors. And there are a few highlights from this. One of them is, of course, that we need to accelerate the implementation of low carbon buildings and building material to achieve the net zero as mandated by the UN targets, right? And the third one, which is of special interest to me, that they said that by 2030, or rather they pledged that by 2030, 100% of new buildings must be net zero carbon in operation, and embodied carbon must be reduced by at least 40%. So if you can reduce the embodied carbon of the most widely used construction material, which is Portland cement-based concrete, we will definitely move closer to this target, to this reduction target by 40% by 2030 and beyond, right? So we need to take a very proactive step in achieving this kind of milestones. Early this year, Australian Research Council, the Australia's National Science Agency, together with the Research Council, came up with a CO2 utilization roadmap. And I was actually very privileged to be one of the expert interviews while preparing this on the topic of carbon sequestration in cement and concrete. So based on that, they actually strategized three type of goals. One is the immediate goal, the short-term goal, and the long-term goal, depending on when they want to achieve it. And in all these cases, you will see a common objective, which is basically to reduce the CO2 footprint of concrete through different mechanisms, for example, CO2 curing in aggregates, or even integrating CO2 in cementitious building products, or rather achieving carbonate mineralization through CO2 incubation in cementitious building products. So that is a way that we can also achieve local circular economy, because we are capturing the emissions from different industries and sequestering it in cementitious building products. And of course, very recently, the European Union says that, well, nature cannot pay for all the anthropogenic activities leading to high CO2 emissions. So we must target to solve this kind of issues through a range of policy measures and technology measures. So that is a very emerging area, how we can develop low carbon materials for our future cities. So the approach that I took in collaboration with the researchers from the University of New South Wales in Sydney, and we published a couple of papers in this area, achieving carbon sequestration through a combination of biochar and fly ash, and also taking an approach of internal and external carbonation through carbon absorption in the pores of biochar. Right, the chemistries involved are totally different, because in one case we are talking about pumping CO2 into the concrete, and in another case we are talking about absorbing CO2 in that mixture even before mixing in the concrete. So these schematics can actually better help to understand how this can be achieved. So this is the material composition. This can be different depending on the type of admixture being used. So in this case, biochar and fly ash are used, and biochar is mixed under two different conditions. One is that the CO2 is absorbed in a micropores of biochar even before deploying it in cementitious composites. And the secondly is biochar is mixed as produced after necessary processing, and the CO2 is pumped into the concrete, and that triggers a series of carbonation reaction through different mechanisms. As you can see in this ACM, it's ACM showing that the carbonation products has actually formed in a macropore, in a macrocapillary pore in the cementitious matrix. And this kind of deposition is actually beneficial because that reduces the permeability and porosity of concrete. So there are three different objectives. One is to increase the carbonate mineralization. That means to sequester more CO2 in the cementitious matrix. The second is, of course, not affecting the strength negatively, and if possible, improve the strength through this mechanism. And finally, improve the durability, reduce the permeability, and reduce the carbonation shrinkage of the final composite. So here are some findings. So we used peanut shell biochar, which is industrially produced in Australia in large volume. And this is very different from wood-based biochar. And shortly, I will come to the reason why. It contains a lot of nitrogen, because you know that there is a lot of leguminous bacteria, leguminous microbes in such kind of plants, and they fix nitrogen in the root structure of the plant. So that is inherited by the biochar also, and you see a relatively high percentage of nitrogen if you compare this to wood waste or other kind of waste. The carbon content is lower, it's 56% compared to 70 or 80% in case of wood waste. However, the most striking part in this is that of the sodium oxide and even the phosphorus oxide. These are likely due to the salt content that are actually used because some of these peanuts are actually soaked in salt solution to make it more tasty before packing it and marketing it, and some salt content may actually be inherited during this process before the shells were actually taken off. So if we look at how we can achieve this carbon sequestration in biochar fly ash mixes, there are a series of reactions that take place. First, we have to understand there are two mechanisms. One is the liquid-solid interaction, where the carbon dioxide, or sorry, I think I made a slight mistake here. It should be liquid-gas interaction, where the CO2 is dissolved in the pore solution, and then it can trigger the formation of calcium carbonate. And that is also associated with accelerated drying and loss of moisture. The second is the gas-solid interaction, where CO2 directly reacts with hydration products like CaOH or even the calcium silicate hydrate to form calcium carbonate, right? So this takes place in a rather dry kind of mixture that the CO2 can penetrate easily and trigger the sequestration or mineralization of carbonate. How can we quantify it? Well, one of the most widely technique is that of thermogravimetry, that we can quantify the formation of CH based on the decomposition temperature ranging from 420 degrees to 540 degrees, and we normalize it with respect to the original weight of the dry cement paste. The another way is the calculation of CO2 uptake, which is actually indirectly calculated from the decarbonization, or rather you can call it the decomposition of the calcium carbonate in the mixes, which ranges from 550 degrees to 950 degrees when you are talking about calcium carbonate. So there are two types of calcium carbonate usually formed when you are talking about accelerated curing. One is the less crystalline or poorly crystalline carbonates such as aragonite and vaterite. These are the mineral names, which tend to decompose around 540 to 720 degrees, and the well crystalline carbonate, which decompose between 720 degrees and 1000 degrees, because they have a very well formed crystal structure and therefore more stable in nature. So there are two ways how we can actually quantify the CO2 uptake. We can subject the samples with biochar and fly ash with different combination, biochar added at 1% and 3% by weight of cement, and then together with fly ash to replace 20% of cement. And you can see the rate of mass gain that takes place due to the carbonation. If you are actually putting the samples in a carbonation chamber, in a tightly sealed chamber with a certain percentage of CO2 being pumped in, you'll initially see a drop in mass. And why this happens, you probably remember at this point I talked about the gas-liquid interaction that actually is associated with the loss of moisture. So this is the loss of moisture taking place in a very accelerated manner in the initial 3 to 4 days, and then it follows an increasing trend which shows the conversion of CH and other hydration product is taking place into calcium carbonate, right? So in case of plain water, you can see that that increase is 0.12% if you compare to the bottommost part here. However, if you are having biochar in the mix, that increase is about 0.56%. So having biochar in the mix can actually increase the rate of carbonation, which is visible from the rate of increase in mass in this case. Right. If we are talking about the carbonation depth, which can be actually measured using phenolphthalein as an indicator, it, however, shows that having biochar actually reduces the depth of carbonation compared to plain water. And that happens due to the filler effect of the biochar, that the carbon sequestration can actually happen in the top few layer of matured concrete. A more quantitative technique where you can actually find out how much CO2 or how much mineralization has taken place is through thermogravimetry again. So you can actually categorize the formation of calcium carbonate into two categories, like 550 to 720 for the poorly crystalline calcium carbonate, and 720 to 1000 for the well crystalline carbonates. And you can find out what is the net carbonate mineralization based on the comparison with that of a background sample, which is uncarbonated. So it shows that the net carbonation, even after taking into account the standard deviation, is increased by 10% in case of the biochar paste and 18% in case of the biochar fly ash pastes. Why this happens? There are two reasons. One is that the pores of biochar actually give way for the penetration of CO2, and also the hydration products that are formed in the pores of biochar are also carbonated consequently. In case of the biochar fly ash mixes, that is more porous in nature because we are replacing 23% of cement, which is causing higher dilution and therefore higher porosity. The rate of CO2 sequestration is higher. So if you convert this into the amount of CO2 uptake, you can see that we can facilitate about 14 to 15% of CO2 uptake in biochar cement paste and about 16 to 18% in case of the fly ash biochar pastes. This can be further increased if we do a bit of engineering on the pore structure of the material that my team is currently working on, how we can develop controlled lightweight material and have a higher amount of CO2 sequestration. So the results will be published very soon. If we look under the ACM, we of course see a lot of these carbonate crystals being formed in the pores, and that are also associated with better durability. Right. However, something that we observed, which may actually be addressed quite easily, is that of the reduced hydration of the fly ash particles and the surrounding of it. Why this happens? Because moisture is lost during carbonation, and there is a mechanism or a phenomena called moisture starvation, that sufficient amount of moisture is not available for hydration. Right? So in this case, the fly ash particles are mostly behaving as fillers in the cementitious matrix. So there is a way to address it, which is basically through moisture replenishment for a few days after carbonation. And that can actually trigger a higher rate of hydration and also help in other achieving other durability properties. How does it affect the strength? And that is, you can see the comparison of strength after water curing and carbonation curing in case of the biochar mortar. So compared to control, there is a very definitive substantial improvement in strength that can be observed using biochar even after the accelerated carbonation curing. Right. So we are here talking about the recovery of strength after reweighting, which is something I just mentioned, that if you actually replenish the lost moisture, you can improve the strength development. And if you compare this curve and this curve, you can see that we are achieving about 60 megapascal strength here, which is about 20% improved, or close to about 25% improvement compared to this case where no moisture replenishment took place, right? So this is another way of doing it, that we can actually improve the strength development and the hydration. The other important parameter is that of shrinkage, because carbonation due to loss of moisture and the change in the chemistry of the hydration product is associated with high shrinkage, right? So it is quite visible if you compare the normal drying shrinkage to that of carbonation shrinkage. We can see a difference, or rather increase in shrinkage. So in case of the drying shrinkage, adding biochar actually increase the rate of drying shrinkage compared to control. And that is something very different from that of wood-based biochar. And why this happens, we have to again go back to the fundamental properties of biochar. And you probably remember at this point, I talked about high sodium content in the biochar in this case, which is from peanut shell, right? This sodium is actually from the sodium chloride, which is the salt that was mixed during the soaking of biochar. So if you have a lot of sodium crystals or even potassium crystals, as happens in case of salt, they insert themselves in the CSH layer, right? So due to this insertion, what happens is that there is a high electrostatic force of attraction between these inserted atoms. And that causes the layers to come closer compared to the case of the plain cement paste or plain mortar without the biochar. So that leads to higher amount of shrinkage taking place. So the lesson learned from this was that we must be mindful of the composition of biochar and its origin before using it as a cementitious admixture, because certain ions, for example, sodium and potassium, can lead to high shrinkage, and that is definitely not desirable. So taking a step ahead, we explored biochar-enhanced bio-based self-filling concrete, and that is slightly different from what Dr. Kong is currently investigating using crystalline admixture, which was very interesting to listen to. So this is a different pathway of using microbes to have calcium carbonate being formed and seal the cracks. However, something I want to mention, and that is probably taking a cue from Dr. Kong's talk, that calcium carbonate is a sealing agent, which is right, which is for the surface crack, but it is also a healing agent when it forms in the internal microstructure of the concrete, right? That is confirmed through our investigation and other investigations that have taken place over the last few years. However, the more important point is why use biochar in case of self-filling concrete? Or rather bio-based self-filling concrete. The main motivation is that when you are using microbes or similar other bio-based agents, they're really not stable in the high alkaline cementitious matrix. You can use a lot of spores, but the spores will become deactivated after a few days because of the high alkalinity. They usually survive under acidic environment, which is not the case of concrete, right? The other motivation is that of sourcing for internal moisture. And that is important for both bio-based self-filling concrete and also autogenous self-filling concrete, because you need moisture to trigger hydration, right? So what we did, we took a three-pronged approach. One is that we immobilized the spores of biochar, the bacteria spores in biochar, because the pores of biochar can then act as a shelter for the bacteria to grow and also perform the self-filling action. The second important part is that of the restriction of crack width. Why do we want to restrict? Well, because if the crack width is very large, then of course the sealing products won't be sufficient to bridge across the crack and seal it. So therefore there must be a mechanism to control that. The final one is that of the sourcing for moisture, which biochar can also do partially. However, a more commonly used approach is that of super absorbent polymers. So these are special polymers which can absorb about 70 to 80 times volume of water than their own mass, and can store it without dissolving in the cementitious mixture. So you imagine that there is a rainfall event. The SAPs can actually store the moisture and later supply it for the microbial metabolism and formation of calcium carbonate. So finally, we are evaluating the self-filling through different means. One is, of course, the sealing of cracks, the surface cracks, and the recovery of original properties. And that is very important because we want to recover the strength and the original permeability of the cementitious mixtures, right? Else we are just sealing the cracks, as Dr. Kong rightly mentioned. We are not doing a self-healing of the concrete. So we took an approach and that actually constitutes evaluation under single loading cycle. That means we just damage it, let it heal, and measure the self-filling, and multiple loading cycle approach. So here the flowchart shows how we achieve that. In case of concrete, and that is C60 concrete with close to 60 megapascal strength at 28 day, we damage it at about 60 to 80% of the peak stress at 14-day age. And then we let it heal for 14 days under a dry and wet curing condition, right? Because we always do not have supply to moisture, and that is a very practical scenario. So in this case, the drying regime was about 3 to 4 hours, followed by, the wet regime was 3 to 4 hours, followed by a totally drying air curing regime. And then we find out how much strength and permeability recovery is achieved in the healed sample, and we do so by comparing it with that of the undamaged samples of same age. Then again, we damage it, and then we observe the same, and this cycle continues for 3 stages. So there are 3 cycles of damage and loading involved. And we evaluate it through, of course, microscopy imaging using optical microscope and scaling electron microscope to see how much apparent crack sealing on the surface has taken place. We, of course, find out what is the recovery of strength, water sorptivity, and water penetration through this expression. So the recovery ratio can be quantified from the comparison of the healed sample, the mechanical strength of the healed sample, to that of the undamaged sample at the same age. Thus, we can quantify how much effectiveness we have achieved through the self-healing. So if we look at the apparent crack sealing, we see a very noticeable trend. This top part, this cluster marked by this blue dotted line, is that of the combination of BCBS, which actually means biochar and the bacteria added together, right? And here is the sealing ratio being shown on the y-axis. So what it actually means is how much portion of a crack width is being sealed by the calcium carbonate formed due to the metabolism of bacteria. The lower cluster here, which is marked in the red circle, is actually the autogenous self-filling, or if I may call it, improved autogenous self-filling through the combination of SAP, PVA fiber, and also the combination of SAP, PVA, and steel fibers, right? So here we can see a very distinct trend that when you have the bacteria in the mixture together with biochar, it of course increases the efficiency of crack sealing for different ranges of crack width. So we went up to 700 micron crack width in the damaged samples, right? So compared to the autogenous sealing, and as is also established in other research, this kind of mechanism can seal wider range of cracks with a higher sealing ratio. So let's look at some of the visual examples. So here is a crack in case of control. There is no other healing agent. It's just a plain mortar. You can see that the white cracks about 300 to 500 microns are not actually healed, right? Even after some water was supplied during the wet dry cycle of curing. If we have the combination of SAP and fiber, we see some kind of healing for relatively narrow cracks about 300 to 500 micron. However, some part of the wider crack, which is say for example 700 micron in this case, close to 700 micron, is not actually healed. If we compare that to many examples, and here is one of them of the BSBC, the biochar and bacteria combination, we see crack width of about 750 micron being completely sealed by this kind of whitish sealing products. So we actually collected a part of this whitish sealing product and we observed it under a high resolution scanning electron microscope. And what we see is that these sealing products are these rhombohedral crystals, which are calcium carbonate being formed by bacterial metabolism. And here you can actually see a bacteria cell, and that is quite rare to observe, a rod-like bacteria cell formed around the microbes. Here is the EDX spectra, electron dispersive spectra, which confirms the presence of calcium carbonate. It is definitely pertinent to ask, would you live in a building with microbes? And that is a question I was also asked during my PhD very often. The answer could be both yes and no, right? And why it may be a yes, because in many cases we want to consider whether the microbes are harmful to humans. And that is very, very important given the current ongoing pandemic. And this kind of microbes are actually categorized as very safe by the international body. I do not recall the name at this point, but they do categorize the microbes in terms of their effect on humans, right? So that's how we select bacteria. There is another point to it, and that is we do not have to restrict the application to just buildings. It can be other infrastructure such as marine applications or even pavement applications, right? So we do not come in direct contact with that. And in certain cases, there are also ample supply of moisture, for example, in case of the intertidal zone for coastal applications. So moisture is also beneficial for autogenous healing and also bio-based healing. And in that those cases, the healing can take place quite effectively through bacterial metabolism and maintain the water tightness of the concrete structures, right? Now coming to the recovery of softivity and penetration, here I'm showing the softivity after cycle 1 of healing and cycle 3 of healing respectively. And on the y-axis, the softivity is shown. So higher the softivity means more water is penetrating through the capillary action with respect to the time of exposure. So you can see that after the first healing cycle, the difference in softivity or the reduction in softivity is only about 20% compared to plain concrete due to our material combination. When we go to cycle 3, this reduction is much, much more prominent, is about 70%. Why this happens? Because when we continuously damage the concrete again and again repeatedly, the cracks in plain concrete is not actually healed. And those cracks act as the intrusion point for the moisture to go in. In case of the bacterial biochar combination, the metabolism can still contribute to the sealing of cracks through calcium carbonate, and that's how it prevents the penetration of moisture deep into the concrete. So as you can see, the benefit of it, that after repeated healing, it is just cycle 3. It could be probably cycle 2 million, 3 million in case of actual concrete structures. That is an encouraging indication that this can retain the integrity of the structure in long term. What about the water penetration? As I probably explained earlier, the penetration takes place under high pressure, about 6 to 7 bar. We modified the pressure, well, it's 6 bar in this particular case, and we measure the depth of penetration from the exposed phase of the sample, right? And based on this test, we find that after third cycle, the material combination can lead to about 60% reduction in penetration depth. And that is very encouraging, because in that case, we're reducing the penetration to only a few mm of the cover concrete, and we are protecting the reinforcement still. In case of the plain concrete that you can see in this case, this cluster of bars, it's much higher, right? It's about 15 to 16 mm. So the recovery will also be low. But how does it achieve this kind of sealing or better sealing? So we did extensive microstructural study of the healed concretes, and we find several important attributes to it. One is that when you use fibers, you can imagine that under loading, the zone around the fibers are actually stressed, and the cracking takes place around the zone, although the fiber can actually help bridge the cracks and limit its width. However, these micro cracks can actually be point for the water penetration and absorption. So having biochar can actually seal, or rather fill, the areas around the fiber matrix zones, and you can see several cracks in the biochar taking place. Why this happens is because biochar itself can actually act as a crack pinning admixture. What is crack pinning? Is that because biochar property is different from that of the cementitious matrix, it's a much softer particle compared to cement matrix. It absorbs the energy necessary for crack propagation, and it limits the propagation of crack into the cementitious matrix. And that you can see in this case as well. The biochar particle is cracked, but it prevents cracking in the zones around it. So it has a kind of cushioning effect, as you can call it, because the crack or the dissipation of the energy takes place due to the addition of these heterogeneous biochar particles. What role does the fibers play? And that really depends on the type of fibers being used. In this case, we used PVA fiber, which is hydrophilic in nature. And you can see that the fiber surface also acts as the deposition site for the biomediated calcium carbonate. And the precipitation of the carbonate also takes place around the fiber zone, which actually densify it like the aggregate matrix zone and reduce water absorption and water penetration. We also did see some internal crack sealing in the internal part of the cementitious matrix due to these rhombohedral crystals, as you can see in these cases, and that also contribute to higher recovery of durability and strength, because they densified these otherwise open cracks. So that you can see in case of the recovery of strength. We also did a recovery of stiffness study, although the graph is not here. However, the trend is very, very similar. So in case of the biochar bacteria combination, after the 3 cycles of damage and healing, the recovery ratio is 18% higher than in case of the control, right? So this shows a very promising potential of having this kind of material combination as a self-filling supplement, right? So in the first cycle, you can see that the control definitely shows a higher recovery ratio, but it diminishes as repeated damage is inflicted. However, the biochar bacteria mix, well, it does show some reduction. However, it maintains a higher recovery of strength after this multiple damage cycles. So here are some of our publications over the last few years in the area of self-filling. We did a collaborative research with the University of Colorado, Boulder, and this study is published in Cement and Concrete Composites, where we used 2 types of SAPs, superabsorbent polymer. One is, of course, the commercial polymer that is available off the shelf, and another was a kind of polymer that was manufactured in the lab from algae, right? And it is also a biosource, and we also push the application of bio-based material. So this also shows a very promising potential of achieving good self-filling through this kind of different superabsorbent polymers, right? Very recently, I think the publication is already online. I authored another article comparing the autogenous and the bio-based self-filling technique in fiber reinforced mortar with hybrid fibers. So this is also published, and there we compare how having biochar bacteria can improve the self-filling recovery. You can also refer to our review papers published a few years ago in the Journal of Construction Building Materials and Materials in Civil Engineering, where we discussed the bio-based self-filling, and we also talked about the encapsulation technologies and how they help in achieving high self-filling effectiveness in concrete. So here are some future directions that I think will help to push the application of low carbon materials and smart composites. And one of them is an interplay of policy framework and technology, right? We cannot have just one of them because we will keep on developing material compositions and new materials. However, they won't be implemented in field. So we also need a strong policy framework to push implementation of this kind of new technologies to site. Another is the total evaluation of novel building materials. We always talk about new admixtures recovered from waste streams. However, it is very important to also characterize them from the environmental perspective. Why is it important? Because you know that some admixtures are also rich in heavy metals and other toxic compounds, and that can actually cause harm to the environment, to the groundwater, to the air quality. And Singapore is very, very strong and particular in that aspect. Probably Dr. Kong can also vouch for that every drop of water that falls on Singapore is precious. And therefore, a very stringent environmental characterization of all building products take place before their implementation. So I think in India, we should also practice that. We have a total performance evaluation, and that kind of framework should be implemented. There are other sources from local waste streams that we can use. For example, alkali activated material, magnesium cement from waste brine, glass fines that can actually be used to replace part of the coarse and fine aggregates in cement-based construction materials. And that can actually widen the boundary of development of sustainable materials in long term, right? We should focus more on multifunctional application of building materials. We should not just see through a narrow lens for building application. We always can develop new materials made of ceramics, cement, and other alternative binders for environmental remediation and filtration. These are just some of the examples, but of course our imagination can go well beyond. And finally, the bio-based smart materials and sensors, and this is also an emerging field of research because if you look at the typical sensors being used, there are of course commercial sensors made of copper, made of steel, but we are also focusing on CNT, like carbon nanotubes and carbon nanofibers as sensors in structures. Of course, they do function well, but major limitation is the cost and the energy involved. So the bio-based materials can actually be a potential source of such sensors, and we can use it for smart functionalities in buildings. So with that, I conclude my talk. I'll be very happy to hear from you, any question and clarification that you may have. Thank you.
Thank you, Dr. Souradeep, for your pioneering work, and through your company now, you are doing such a great work in sustainable material and development in this regards. So one of the queries which was there is from Mr. Rahul Dandotia. He's asking that, thanks, first of all, he's thanking for sharing the in-depth study. He's asking, what is the possible expected effect of ambient temperature on use of biochar?
Okay, maybe I just seek a quick clarification. When we talk about ambient temperature, does it mean the ambient temperature of biochar concrete where it is applied? For example, the air temperature, right?
Yeah, air temperature. Yeah.
Like based on different climatic zones, I believe, in India. Well, that's a very good point. We actually did some incubation studies on biochar concrete in a wide range of temperature from about 30 degrees to up to 70 degrees. And as you may know that when you elevate the temperature, the hydration reaction is actually accelerated, right? It may both be good, can be bad as well, because we are talking about mass concreting, and if the temperature is very high, it can cause certain thermal cracking in cementitious mixtures, right? So there are ways to address that, definitely. But if you are talking about the strength development or even the durability of biochar concrete, those are not severely affected. Probably I will ask Rahul to refer to one of our publications where we tried or investigated biochar concrete under elevated temperature, at very high temperature, about 300 degrees or even 550 degrees. And that shows that having biochar can actually improve the recovery of strength at high temperature by providing some pressure valves for the escape of the moisture, so that steam pressure does not build up, and it helps in having higher strength development. But okay, let's look at the other spectrum, which probably could be the freezing and thawing cycle. If you're talking about application probably in Kashmir or even parts of Himachal Pradesh, right? The temperature can go to sub-zero during the chilly winters. So we must do more investigation that is not being done as far as my knowledge goes. We are focusing on mostly the normal temperature as we expect in Singapore or even in Australia or even in my city in Bangalore. So the temperature doesn't go below 18 or 17. So we must look at those kind of temperature as well, about probably 4 or 5 degrees or even sub-zero, and see how biochar concrete behaves. So that could be a potential area of research. Thank you.
That will be a really good area. Even I was thinking to ask you about the same, because we are having a lot of freezing and thawing issues in Himachal and Upper Himachal especially.
Right,
so
right, exactly.
There are the structures. Maybe somewhere we can discuss and do a collaborative effort.
Definitely.
That we can have a structure.
What makes biochar very interesting is that porous nature. When you have a porous admixture, you can use it for different applications, right?
Yes.
You can see the lightweight aggregates, how people have actually exploited it for different kind of, smart functions. So definitely there is a potential, I believe, for this kind of temperature range, sub-zero range.
Yeah. One another thing in context of Himachal, how is the application of pine needles and such kind of waste which we are generated and from the forests which we are getting can be applied, and how can the results be?
Okay, when you are talking about feedstock, we actually must characterize it after turning it into biochar, right? And that is very important. All biomass is made up of carbon. This is the fundamental composition. However, the percentage of carbon will vary. But the more important aspect is the inorganic composition as well, right? So if you're talking about pine needles, we need to see what are the other ions and compounds are present in this kind of feedstock, right? So if it is within the acceptable limit based on our past investigation, definitely it can be used after the necessary processing, I believe. Nothing stops any kind of biomass being turned into biochar and used in cement. So there is a potential,
Because the studies which NIT Hamirpur and some other institutes in Himachal have done, they have found it a very flammable material. So from that point of view, how it will work out?
Yes, flammability is a widely discussed topic, and there are, I think, some studies published by University of Edinburgh in this aspect, flammability of biochar, right? Flammability depends actually on the preparation condition of biochar. Let me give an example. If you are producing biochar at 200 degrees or 300 degrees, you still obtain the black solid, but it does have a lot of oxygen containing groups on the surface from the cellulose and hemicellulose. Those kind of biochar are definitely flammable because the groups that are present are extremely labile in nature. However, when you are increasing the temperature to beyond 450 or 500 degrees, you are removing most of the oxygen containing groups, and that makes the structure of biochar more stable and less flammable. However, we must not constrain ourselves to this kind of theory, because the inorganic composition is also important, as I shared earlier. So definitely it must be tested for flammability as well. So we did a very simple test of exposing some few grams of biochar to fire, and we tried to see whether it catches the fire when exposed to it. So we found a similar trend that high temperature biochar are less flammable. However, probably Dr. Gupta, you will want to take note that for some manufacturers, they turn biochar into pellets when they ship it. That is not really linked to the flammability directly. However, it is linked to the high surface area of biochar. So if you have tons of biochar in one place and biochar has extremely high surface area, they can react with air, right? And that can actually trigger some kind of flammability event, the biochar. So the storing is also something we must take into consideration. Yeah.
Yes. So thank you once again, Souradeep, for your such an in-depth studies since your graduation days. I guess you are doing in the same field, and now you have founded again your company. So we are actually really grateful to you to
no worries. I'm
event.
very happy to participate in this, and yeah,
and give you
if I could, also encourage the students to take a path of research and entrepreneurship.
I wanted to ask in that regards also, how was your journey from NUS to Australia and then back to India in IISC? What message you can give to our students also, so that they pursue higher knowledge?
I was in Singapore for long 11 years, so it is not just during my PhD. And one of the benefits you have when you move to a different country is that you step out of your comfort zone, right? And that is a very big learning experience that one can have, right? So I always encourage, even my students to go and explore the world. And that is a lot to learn from. How people work, what kind of values they have, even what kind of policy measures are there at the top level. And that is very relevant because in today's world, we are talking about technology and policy simultaneously. One cannot survive without the other. So these kind of things we must learn, and we also should keep an open mind, right? So when we step out of India, we tend to think in a certain way. I mean, that is not wrong. I mean, that is the default line of thinking. But we also must be open to receive other viewpoints and feedbacks, that we see, the good part of it that we see in other places. So I believe from my personal experience, it has been very enriching during my time in Singapore. I've learned a lot from the amazing faculties there, from very friendly population. And I'm very delighted to see Dr. Kong around here, my colleague from my alma mater. Very happy. So yeah, that's a great learning experience. And then when I went to Australia, things are all, again different. How people work, it's not totally the same. The work culture is vastly different, right? So you must suit yourself and remain productive and relevant, right? So in today's world, we talk about two things. One is relevance, and another is the resilience. And these are two important traits even for a person, right? So you always must be receptive. We must stay relevant. Our research must reflect or address the global concerns, right? So it's very important to do a ground research and proceed in that direction. Later, when I moved to IISC, early this year, that is again different because I'm setting up my own lab. I'm starting new programs in different areas like additive manufacturing, low carbon materials. So I have to lead my group. So it is always a learning experience. I learn from my other colleagues at the department. They help me, they support me. So we can always make progress if we stay open. So that is, those are the lessons I would like to share.
Yes.
Yes, and very importantly, we always must think about the relevance to society, the impact that we have. CST at IISC has done a lot of translational research. They have moved to the society from lab and applied that. And that's a very good, enriching experience when you see your inventions being applied. And that is one of the factors that even motivated me to initiate this startup. Because if you do not care about commercialization of your invention, probably nobody will. I mean, you are the inventor, you are the initiator, right? So we always should think about the implementation and relevance. Yeah.
Because Himachal government also takes sustainability at a very high stake, be it the tourism destination of India, and they have given some certain guidelines, and as plastic ban initially, they are the inventors of it in Indian regions, and again, due to these policies and the researchers like you who are promoting sustainability through various products, we are leaving a legacy for the future generation to come. And this is how step we are taking closer towards the goal of this conference which we are having.
Yeah, we should. I mean, we may fail. I mean, nobody knows whether you will succeed or fail, but you take the first step and see how things, fold out. Yeah, we never expected the COVID to happen, and that has drastically changed the landscape for both commercialization and research. So it's a different set of challenge, but we try as best as we can. Yeah.
Thank you once again, and Dr.
Yeah.
Souradeep, for taking out so much of your precious time and delivering such a great keynote.
Yeah.
talk.
Thank you, Dr. Dhanmay. All the best with the rest of the conference.
And I also thank once again all of the distinguished participants who have been patiently listening even after we going above more than an hour from the expected time. So next technical sessions we'll be starting at 2:30 p.m. So all of the registered participants in technical session 2B, 2A, and 2C will be going to their respective virtual classrooms from 2:30 p.m. with their session chairs. And then we'll have another sessions of keynotes, keynote 3, keynote 4, keynote and 5. They are scheduled from 3 p.m. to 6 p.m., including the industry keynote from Mr. Arpit Mehta. Then from 4 to 5, we have keynote from Professor Sandeep from IIT Roorkee. And then the last keynote for the day will be given by Professor Sandeep from IIT Indore. So we'll be hoping to see you at 3 for next events. And till then, you can please have your lunch. We are sorry for the delay in the schedule, but it was such a vast learning experience, so things got a little delayed. Once again, we thank you and hope to meet you at 3 sharp. Thank you so much.